the Gulf Stream is going from North America and heating Europe, it has to, somewhere the water has to go down. And the fact that the water is cooling off and getting heavier plays a role there. But in the ocean, there's another quantity that determines buoyancy as well besides heat, which is salinity. We all know that salt water, everything else being equal, salty water is denser than fresh water. And you get the formation of salt water in equatorial regions because of evaporation, which the moisture goes into the air but leaves behind the salt, leaves it saltier, but it's very warm, and then you get warm salty water and competing with cold fresh water there. On an even larger scale, I don't know if you knew this, but convection and buoyancy forces are the cause of plate tectonics and continental drift. The Earth is to leading approximation, is a 6,000 kilometer radius ball. The first 1,000 kilometers of radius is what's called the inner core. It's a solid ball of heavy metals like iron. The next 2,000 kilometers is what's called the liquid core. It's liquid metals, liquid iron. And the top 3,000 kilometers is what's called the mantle. Now, the mantle to us is rock, but if you live on a geological time scale, this rock flows like a fluid. And due to both primordial heating from the formation of the Earth, where there's a lot of heat in the center, and ongoing heating in the mantle due to radioactive convection, which is radioactive decay, which is about 80% of the heat source there, you get convective currents in the mantle that then on the surface, just like the atmospheric convection makes wind on the surface, that drags around the continental plates and causes continental drift there. In the liquid core itself, now of course, let me just say that the fluid properties of rock are rather extreme. It's very high viscosity, although it has relatively good thermal conductivity, and we'll see how that extreme nature of the parameters there plays a role in the heat transfer. The liquid core in the center is very interesting. The convection, the stirring up due to both thermal convection and compositional convection, that is that different minerals are being dissolved into the liquid core, which change the buoyancy force and change the buoyancy-driven flows, that generates the Earth's magnetic field through a dynamo effect. Now, the Earth's magnetic field, just like we couldn't live without atmospheric convection that was bringing moisture into the land, we also could not exist without the Earth's magnetic field, because the Earth's magnetic field is what protects us from the solar wind of high-energy particles that the sun is showering us with all the time. It's the Earth's magnetic field that deflects those. If we didn't have a magnetic field, we would be irradiated. This would be a sterile planet that we live on, for sure, there. And at even larger scales, convective heat transfer is one of the major players in stellar structure. A star is an ongoing thermonuclear reaction trying to blow itself apart, but the material is all being sucked back together by gravity, and it's that balance that determines the structure. And getting the heat out, getting the released energy out is the name of the game in stellar structure. And the outer shell of stars is where the matter is cool enough that, well, it's cool enough that it's a plasma. It's a plasma, so it's not a regular fluid, but it's where the electrons and the protons are separated from one another, but it still has fluid properties. And the dominant heat transfer mechanism at that level is by convection, is by the carrying of the material. Of course, the convection here is very complicated, because if you have a plasma, then electromagnetic properties are extremely important, and the interplay with magnetic fields and things like sunspots play a major role in stellar convection there. Now, if you've ever looked at the surface of the sun, which your mother probably told you not to do, but I think even Galileo did a long time ago, you're familiar with the fact that the surface of the sun has a very granular structure. And if you look closely, you see this roiling and boiling structure that's very reminiscent of a fluid boiling or a fluid convecting like this. Now, the first experiments, laboratory experiments, to try to understand these kind of flows, these kind of fluid flows and their transport properties, was done in 1900, over 100 years ago, 116 years ago, by Henri Bénard, who's a French experimental physicist. And what he did was he took a thin layer of fluid and very carefully heated it very uniformly from below. And because when you get density variations, you also have slight variations in the index of refraction, then if you shine light on through the fluid in the right way, you can see patterns. And we've all seen this. On a hot day, you can see the heat rising. You can see the heat rising. Actually, you're seeing density variations amplified through index of refraction variations by light there. And he saw patterns like this, which were not unreminiscent of patterns on the surface of the sun. Now, that was in 1900. Now, nowadays, if an experimentalist was the first person to discover something like this, it would probably be 16 hours, not even 16 days, 16 hours before a theory appeared on the preprint archive explaining what was going on. But back then, it took 16 years. And the first theoretical attempt to discuss this was by Lord Rayleigh, John Strutt, and a paper was published in December of 1916, so almost exactly 100 years ago. And this is a beautiful, beautiful title, the kind of title that Physical Review would never let you use these days. On convection currents in a horizontal layer of fluid, comma, when the higher temperature is on the underside. It's a beautiful title. And this is a fantastic paper. I'll remark more on this here. Now, Rayleigh's model was very simplified. He wanted to get at the essence of this phenomena. And so what he said was, the model is going to be that we have a fluid confined between two rigid plates, and the rigid plates are perfectly conducting, and the bottom plate is being held at a hot temperature, and the top plate is being held at a cold temperature, and we want to determine what are the conditions, the material parameters and the temperature gradient and the geometric parameters that determine when the fluid will flow, when the fluid will flow, and what will be the nature of the fluid flow. Now, it's quite interesting. This is an interesting historical note, is that actually Rayleigh's model does not model Bénard's experiments. It wasn't until the 1950s that it was really completely sorted out and recognized that the patterns that Bénard saw were not due to buoyancy forces. Turns out his layers were too thin and the density differences were too small. They're actually due to the fact that he had an open surface on the top, and it was surface tension variation with respect to temperature that caused the instability that drove that flow. Nowadays, we call this Marangoni convection, Bénard-Marangoni convection. And actually, that was figured out by somebody who worked for a paint company. If you've ever painted anything, you know that if you put too thick of a layer of paint on something and let it dry, it often dries with ripples in it. Those ripples are appearing because during the drying process, you have the evaporation of the solvent, and the evaporation is a cooling process. You have cooling from above, and you have this instability due to temperature variation of surface tension that causes those ripples to dry in there. Anyway, despite the fact, well, one way we know this is that when you actually do what Rayleigh suggested, you don't see this nice hexagonal pattern, honeycomb pattern. You see a pattern of straight parallel rolls. So this picture actually, you see straight parallel convection rolls like this. That's the primary instability there. But nevertheless, we still call this Rayleigh-Bénard convection, even though that's strictly speaking a misnomer. And here's just a shot of the kind of patterns that the most simplified version of buoyancy-driven flows will induce in the atmosphere here. So it would be on a relatively quiet morning when the Earth got hot enough, started to get these large-scale convection rolls, and the clouds are just patterning where the upwelling and the downwelling are at some altitude there. Okay, here is I'm going to show a few equations to give you a flavor of what you can all handle this of what the mathematical model is. As I said, Rayleigh wanted to have a minimal mathematical model. So he considered a fluid confined between these two plates at z equals 0 and z equals h, so the layer height is h. And he wanted to have the fewest variables he could deal with to describe the phenomena. So he needs a temperature field, so the temperature as a function of space and time in the fluid. He needs a velocity vector field for the fluid, so he has to say what is the speed at which each fluid element as a function of space and time, what's the speed with which it's moving, and he needs a pressure field inside the fluid at each point in space and time. And then he needs some boundary conditions, and he sets the temperature as hot at the bottom, cool at the top, and there's no fluid flow. So the velocity field, this is the tradition in fluid dynamics, is u, v, and w are the x, y, and z components of the velocity field. And there's no flux of fluid through the boundary, so that the fluid can't carry the heat into the boundary, it can carry it to the boundary there. And then he needed equations of motion that coupled these things. And in his paper, he says very nicely, the calculations which follow are based upon equations given by Boussinesq, which I will show on the next slide. They are a combination of the Navier-Stokes and heat equations. Who has applied them? Here it says, the special limitation which characterizes this approximation is the neglect of variations of density except insofar as they modify the action of gravity. In other words, we know that the density has to vary in order to have a buoyancy force, but he's going to neglect, the density variations are on the order of percent, let's say. So he's going to neglect density variations everywhere except in the buoyancy force term. You'll see how that plays out here. So this is going to be convection by an incompressible fluid, but subject to a buoyancy force. Okay, so here are the equations of motion. Now, there are many parameters here, and I'll discuss that in a moment. Rho is the density of this incompressible fluid. C is the specific heat. T is the temperature field. So the top equation says that the rate of change at a point of the thermal energy density is the divergence of a heat current. So J is the heat current. And the heat current has two components. Well, it's proportional to the density and the specific heat. It's got one component that's diffusive, so kappa is the thermal diffusivity, and that's just Fourier's law, so that the heat current there is proportional to the temperature gradient. And the other is the convective term, it's proportional to the fluid flow, the velocity there. And then the velocity fluid itself, the velocity field itself, satisfies the Navier-Stokes equations, which is F equals ma. This is u dot plus u dot grad u is the convective derivative of the velocity field. It's the rate of change of the velocity of a fluid particle when you're following the particle is due to, well, there's the pressure gradient, the local pressure gradient. Then there's the viscous forces. Nu is the kinematic viscosity, and this is the force due to neighboring fluid elements rubbing against one another. So that's a frictional force. And then G is the acceleration of gravity in the z direction. The G usually points down traditionally. K is the unit vector there. Alpha is the thermal expansion coefficient. So G times alpha times T times the departure of T from some reference temperature is the buoyancy force. It's the buoyancy acceleration, actually, there. And then otherwise, the velocity field is divergence-free, which means the fluid is incompressible. So this is the basic, this is what's called the Boussinesq approximation, which preceded Rayleigh, these are the equations he's using there. Now, what we want to know is the heat flux, the vertical heat flux, how much heat is being carried by the fluid. So we look at the z component of the heat flux vector here, which has two terms. One is, again, that diffusive term, Fourier's law, and the other is the convective term. Now, here the angle brackets are going to be space-time average. So I'm going to average this. There's going to be fluctuations in the heat current in space and time, but I want to know on average over my fluid sample and over time, I want to know what the vertical heat flux is there. So the two terms, the first term now, we can do a little calculation. You can do this in your mind. I'm taking the spatial average of dt dz. That means I'm integrating over x, y, z, and t. Well, the integral with respect to z of dt dz by the fundamental theorem of calculus is just t evaluated at its two endpoints. So the first term, no matter what the fluid flow is, gives you a conductive heat flux that is exactly what you would get just using the material properties of the fluid, not concerned with the flow. So that's the conduction current. And then the other term, which is proportional to the correlation between the vertical velocity and temperature, that is the convective term, and that's the part due to buoyancy there. So the task of Rayleigh and the rest of us is to determine the JZ that results from buoyancy. Now this is where a lot of confusion ensues, because some people think I'm talking about Jay-Z and Beyonce, and I don't know if any of you know who those people are, but this has nothing to do with those people. Okay. Anyway, there are lots of parameters in this system. In fact, 10 parameters. Now, in Rayleigh's paper, he was old school. So throughout that paper from 1916, he carries all these parameters through in every expression there. 10 parameters. There's the height and the width of the layer. There's a reference temperature. There's the temperature drop. There's gravity. Then there's the material parameters of the thermal diffusivity, density, viscosity, expansion coefficient, heat capacity. But it turns out there really are not 10 parameters in this problem. There are really just 3 parameters. And through the magic of dimensional analysis, we can reduce the equations without losing any physics to a 3-parameter problem. The first parameter is what we now, as I said, Rayleigh did not go dimensionless. He stayed dimensional. We now call what's considered the primary control parameter, we call it the Rayleigh number. Rayleigh did not call it the Rayleigh number. That would not have been proper. And the Rayleigh number is this combination of parameters. It's G alpha times the temperature drop, H cubed over viscosity times diffusivity. In the numerator there is something that is proportional to the magnitude of the buoyancy acceleration, or the buoyancy force applied. And in the denominator are these damping coefficients. This dimensionless number is driving over damping. It's a natural control parameter. It's telling you how hard are you stressing the system in a non-dimensional sense. Then there's another dimensionless number called the Prandtl number, which is a property of the material. It's the ratio of the diffusion of momentum, which is the viscosity, to the diffusion of heat, kappa, there. So this is different for different materials. Air and water have Prandtl numbers that are order 1 to 10. The Earth's mantle has a Prandtl number that's about 10 to the 23rd, which is approximated as infinity in applied mathematics. Oils have Prandtl numbers of thousands. Liquid metals have Prandtl numbers of 10 to the minus 2. So Prandtl number can range over many, many orders of magnitude, but for a given fluid, we consider it to be fixed there. And then the other parameters in the system are geometric parameters. Describe, say, the aspect ratio of the system. If I say that the height is equal to 1, then the width of the system would be the aspect ratio. So different, and of course, if you have different shape domains, you worry about the shape parameters there. Okay, now for the heat flux, we want to know Jz, and the dimensionless measure of Jz that's natural is to measure the full vertical heat flux, including convection and conduction, in units of the conductive heat transfer, because the conductive heat transfer doesn't depend upon the fluid flow. That's just Fourier's law there. And in the dimensionless units, then this is called the Nusselt number. Nusselt was a German engineer, mechanical engineer back in the 19th century. The Nusselt number is 1 plus the correlation between the vertical velocity and temperature. So this is sort of it's a nonlinear PDE that has very complicated solutions, and what we want to know is this correlation amongst several of the variables as a function of the parameters in the problem. That'll tell us what's happening there. So the challenge then, we think of the Nusselt number as being the output. If we're given a given situation, we're given a Rayleigh number, given a Prandtl number, we're given the geometric parameters there, what we want to know is the Nusselt number is a function of those things. Okay. Now, what did Rayleigh do? In 1916, what he was concerned with was the onset of convection. He was concerned with what were sufficient conditions for the fluid to start flowing. Now, it turns out those equations that I wrote up, those Boussinesq equations with those boundary conditions, have a very simple solution, which is, I'll call the conduction solution. It's where the fluid is not moving, so U is equal to 0 everywhere. The temperature then just becomes a linear temperature profile across the layer, from hot to cold, from bottom to top. And the Nusselt number, by definition, is 1, because it's just purely conductive heat transfer. And what Rayleigh had to do in order to solve the linear in order to do the stability problem, the stability of that solution, was he had to provide enough boundary conditions for his problem to do what's called linear analysis, linear stability analysis. Look at the growth rate of small perturbations about that exact solutions. Now here's a point where I haven't told you everything. What we also have to consider are, in order to fully pose the problem, I need to specify boundary conditions on the horizontal components of velocity at the rigid boundaries there. And he says here, we have to also reconsider the boundary conditions at z equals 0 and z equals, that's h. That's h in his old English there, basically at the top and the bottom. Now, what we would like to do in a situation like this, if you have a rigid material boundary, fluid dynamicists would say we should apply no-slip boundary conditions, which means the fluid is stuck to the boundary. That means every component of the velocity vector field should be 0 at the top and the bottom. But he says, and that's what he's saying here. He says, we may still suppose this, we should probably prefer this. But he says, this entails much complication, he says. Now here's an interesting point. What Rayleigh did was negotiated with the physical problem. He's going to throw away a little bit of the physics in order to make the mathematics tractable. And it's going to turn out that turned out to be a very wise decision. So he says, but we may content ourselves with the supposition, well, he says that the second derivative of W vanishes at the boundary. He says, this is equivalent to the annulment of lateral forces at the wall. This is what we now call stress-free boundary conditions. In other words, in his model, he's going to take that the wall is some material such that the fluid can slide across it without friction. That's a stress-free condition. And so this might be a reasonable model, say, for an open surface in terms of the velocity. But for actual hard surfaces, it's not right. Anyway, when he does that, what that means is that to fully pose the problem, he now specifies boundary conditions for the x and the y components of velocities, which turn out to be homogeneous Neumann boundary conditions in this situation. Now he's got a fully posed set of equations and boundary conditions there. And when he solves these, and I'll just say he did the linear stability analysis, which is looking at the evolution of infinitesimal perturbations about that exact solution. This leads to a set of linear constant coefficient partial differential equations, which any of you can solve. It's sort of a high school boundary value problem by separation of variables, and you get eigenvalue problems, and you get and it turns out here that his choice of boundary conditions was such that his primary eigenfunctions were sine n pi z. That's everybody's favorite eigenfunctions, right? Just sines and cosines there. Anyway, what he was able to show was that there is a particular combination of the parameters, which we now call the Rayleigh number. That's why we call the Rayleigh number. And when that particular combination of parameters exceeds a certain numerical value, then that conduction solution is unstable. Moreover, one can prove that when that same combination of parameters is less than that numerical value, that the conduction solution is absolutely stable. So nowadays we would call this a supercritical bifurcation. In other words, below the bifurcation point, absolutely nothing can happen, and above the bifurcation point, absolutely something does happen, and there's no bistability and so on. And he computed this number. It turns out that for his boundary conditions, the critical value of the Rayleigh number is 657. Actually, it's 27 over 4 pi to the fourth, which to 3 digits is 657. Now, it was about a decade later when people started applying realistic boundary conditions. So if you have boundary conditions where one of the surfaces is stress-free and the other's no slip, then the critical Rayleigh number, you still have a pitch for supercritical bifurcation. The critical Rayleigh number is 1100, and if you have two no-slip boundaries, it's 1708. But the picture doesn't change. So here was a situation where instead of struggling with very complicated eigenfunctions and transcendental characteristic equations, he made a little negotiation and was able to capture the essence of the problem there. Okay, so here's the big picture. This is what we think about these days, is what is the Nusselt number, that's Nusselt, as a function of the Rayleigh number, and we'd like to know what this plot looks like. Now, I've plotted this on log-log scale because there's always orders of magnitudes involved with these things here. Well, we know a variety of things. We know that we know that the Nusselt number in Rayleigh's model is always bigger than or equal to 1. In other words, the heat flux is always from hot to cold. The natural fluid flow will never take it the other way. That's good. We also know that the Nusselt number is actually equal to 1. That's 10 to the 0 right there for Rayleigh's less than the critical Rayleigh number for our system. And the question is, well, what happens above this? Well, we know that the conduction state goes unstable. It still exists as a solution of the equations, but it's unstable, so something happens there. Now, at onset, the studying exactly what are the properties of the fluid flow and the heat transfer right at onset near that bifurcation have been one of the most interesting and influential challenges to applied mathematics for the 20th century. In fact, it was exactly trying to understand the nonlinear processes that are going on at onset and the nonlinear saturation that goes on at onset in this model, in this particular model with Rayleigh's boundary conditions, was one of the driving forces in trying to understand what we now call reductive perturbation theory or singular perturbation theory, basically where your small parameter is your distance from your bifurcation point. And one of the early papers that studied this is 1958, Malkus and Veronis, and they were the first ones to accurately compute the amplitude of the convection rolls above, in the nonlinear problem above stability. Now, I would just mention that this first author here, Willem van Rensselaer Malkus, was probably after Rayleigh, was probably the person who was most influential in this field of buoyancy-driven flows and Rayleigh-Benard convection in the 20th century. And he just died. He just died in May, at the end of May this year. He lived a very long and interesting life, and his name will reappear momentarily here. Now, I will also say that Rayleigh's model, with his sort of non-physical boundary conditions, are what a fellow named Ed Lorenz took and did a three-mode truncation of in order to come up with what we call the Lorenz equations these days, which he put on a computer in 1963 and basically discovered chaos, discovered chaotic dynamics. It was exactly, Lorenz was an atmospheric scientist, and he was exactly using Rayleigh's model, an approximation of Rayleigh's model. And both of these things could not have happened unless Rayleigh had made that simplification and changed the boundary conditions so that the eigenfunctions were very simple trigonometric functions. And then later on, Newell and Whitehead introduced the idea of looking at the patterns that one sees in convection at longer length scales. If you drive the system beyond stability, well, at first you get convection rolls, but if you go further, you get short-range correlation into convection rolls, but you get large-scale pattern structure. And the development of this kind of pattern formation and effective equations which define this was again influenced tremendously by Rayleigh's willingness to simplify the model to the point where mathematicians could do things with paper and pencil, didn't have to resort to computers there. Okay, now, what about at high Rayleigh number? What happens when stuff really starts moving? Well, at high Rayleigh number, we get into the regime of turbulent convection. And here is a movie of turbulent convection. See if that'll move. This is from a direct numerical simulation of the full set of nonlinear partial differential equations with no-slip boundary conditions in a can. This is convection in a can. And the color code is temperature. So red stuff is hot, blue stuff is cold, and you see the red stuff is generally rising, the blue stuff is dropping. But what you also see is that you have a pretty much of a well-mixed core. So if I took an average of the temperature across any layer here in the core of this thing, on average I'd get the average temperature there. The temperature drops are very strong at the boundaries. There's a very strong boundary layer, thermal boundary layer down here, and a thermal boundary layer up there, where the temperature goes from being the bottom temperature to the average temperature over a very small layer, shedding all these plumes there. So it's this boundary layer and plume-driven fluid flow, quite complicated. And the question in the business is what's this law? Now, because of 20th century physics, everything's supposed to be scaling, so there should be exponents associated with everything. And the primary assumption has been that there's a scaling law, that the Nusselt number should go like Rayleigh to some power with a prefactor that's Prandtl to some power. And these are the numbers that we'd like to know, because we would like to, if we're doing a general circulation model and trying to understand the climate, you're not going to resolve these turbulent fluctuations due to convection. What you'd like to know is, what is the heat transfer law? What is the heat current as a function of the applied temperature drop? There, you'd like to just have a simple formula for that for your system. Okay, so turbulent Rayleigh-Benard convection. There are theories, there are experiments, and there are theorems. And the field is quite active these days. I'll try to convince you of that. Here's a theory that goes back to the mid-50s. This is, again, from Willem Malkus. Now, his theory said that well, the heat has to get through those boundary layers, so that the rate at which heat can transfer across the whole system is the rate at which those boundary layers are shedding plumes. And the boundary layers are going to shed plumes when the boundary layer, as a convective system unto itself, goes unstable. And so then he applied Rayleigh's stability analysis to the boundary layer itself. This is sort of like a self-organized criticality argument, and said that that's going to be the condition at which I shed, and so the thickness of the boundary layer then is going to determine the heat flux through the boundary layer, and I can sort this out. It's a very simple back-of-the-envelope calculation. The prediction is that the Nusselt number should go like Rayleigh to the 1/3 power, and it should be independent of the Prandtl number. And the independence of the Prandtl number was because the instability in Rayleigh's stability analysis was independent of the Prandtl number there. So that's the having to do with boundary layer dominated plume shedding. But then a decade later, a fellow named Ed Spiegel, who is an astrophysicist, came up with a different argument. He said that, no, really what's limiting the rate of heat transfer across a layer isn't how quickly the stuff gets through the boundary layer, it's how fast a hot plume can fall from the bottom to the top, and how fast a cold plume can drop from the top to the bottom. And so when he just did this kinematic argument and put the numbers in there, and then re-expressed it in terms of Nusselt, Rayleigh, and Prandtl, he got that the Nusselt number should go like Prandtl to the 1/2 power times Rayleigh to the 1/2 power. Now, these exponent differences between 0 and 1/2 for Prandtl and 1/3 and 1/2 for Rayleigh, half and a third are not so far apart, but if you're trying to extrapolate this out 10 orders of magnitude and get an accurate model, then it makes a difference there. So this is what we would like to resolve. And these different exponents have different physics in them. So the competing theories, and after half a century, these are still the competing theories here. I would just say that Malkus's theory also says that the physical heat flux is independent of the height of the layer, because it really only depends upon the boundary layer. It doesn't care where the ceiling is there. Whereas Spiegel's argument says that the heat flux should be independent of the microscopic transport coefficients there. So there's very different physics in these exponents there. What about experiments? People are trying to do laboratory experiments. Currently, there's two different sets of fluids that people are using. One is gaseous helium at about 4 degrees Kelvin, near its triple point, where they can do very carefully controlled thermal conduction studies, because they can vary the ambient pressure and get many orders of magnitude variation in the Rayleigh number there in order to do this. So they're very complicated experiments, very nice. Another set of experiments is being done in sulfur hexafluoride gas at about room temperature, slightly more, but at 15 atmospheres pressure. And these are bigger experiments. The helium experiments, I guess you can't see, there's no human being here, but this is just a regular table. A human that's about as tall as a human being, and the actual cryostat is in there. The gaseous experiments are being done in much bigger vessels, say 2 meters tall, 1 meter in diameter. So there's a human scale. And since they're done at high pressure, you have to put this in a pressure vessel. These experiments are being done in Göttingen at the Max Planck Institute at Göttingen. And then there's even bigger experiments being done in Ilmenau in Germany, where they have a very large can, and inside that can they actually have a movable ceiling, so they can change the Rayleigh number by moving the height up and down. And they're looking at the convection of air inside there and the structure of the boundary layers in that experiment. And there's even been a proposal to use the helium storage facilities at CERN and Brookhaven, let's say, where they use tremendous amount of, in the search for the Higgs boson and all that stuff, they use a lot of helium, and to use their storage facilities as convection experiments. Now, that hasn't happened yet. There are political and economic reasons why that hasn't worked, but there was a cartoonist in the New Yorker who somehow, it's amazing that there's a cartoonist in the New Yorker who also agreed that would be a good idea. I don't know how they ever found a cartoonist who cared about this, but okay, that's that. All right, so here are some data from about 7 years ago, and the data have changed since then, but for my purposes, not substantially. This is Nusselt versus Rayleigh on 3 different experiments over, you notice the Rayleigh number is varying over 6 orders of magnitude, from 10 to the 9th to 10 to the 15th. It's a tremendously large range, and the Nusselt number is going from 50 or 60 to several thousand there. So this is where you get heat transfer that's thousands of times above the conductive heat transfer there. Now, generally speaking, there's good agreement. Oh, let me tell you, these 3 experiments. This is the top one is the French experiment. The middle one is the American experiment, and the bottom one is the German experiment. Okay, I'm serious. Yeah, it sounds like World War I or something. I don't know. Anyway, that's right. And they agree down here, but then at the higher Rayleigh numbers, and we'd really like to extrapolate this out past 10 to the 20th, they start to diverge. And when you look closer at the higher Rayleigh numbers by compensating the plot, tilting it over, blowing up the scale here, you can see the divergence between the French, the American, and the German experiments. And they don't even agree whether or not the exponent is changing or dropping. And I would just mention that the diagonal of this plot, the diagonal line of this plot from this corner to that corner right there would be a 1/3 exponent. So these are all around that 1/3 exponent, but the question is, does it go to higher? Does it go toward the 1/2 exponent? Does it go to something lower? Does it stick around 1/3 there? Okay. So it's fair to say the experiments are controversial right now. They're not settled. The experimentalists are arguing with one another. These are very good experimentalists, several of them in the U.S. National Academy of Sciences, and it's very entertaining to watch National Academy members argue with one another in public. That can be fun. Okay, what about, well, there's room for analysis. There's room for mathematics when we have these unresolved issues here. And what mathematics can do, well, we're not going to solve this problem exactly. The dynamics is too complicated. But what we can do is provide estimates from the PDEs. We can give rigorous limits on heat transfer by analyzing the PDEs. The first work in this area was by a fellow named Lou Howard, who was also at MIT in the 1960s. And Lou Howard, I'll give a picture of him. He just died last summer. And he was also a very influential character in this field. You can see that after a century, you get a change of players here. Well, Lou Howard and a fellow named Fritz Busse, who is somewhat younger and still active, developed a variational analysis, a calculus of variational analysis to determine bounds on heat transfer. And it was about 30 years later, my collaborator Peter Constantine and I developed a method which removed the hypotheses that Howard and Busse had and came up with a method called the background method, which was notable perhaps because the mathematical technology that goes into this nonlinear, fully nonlinear estimate is really stability analysis. And you think of stability and turbulence as being opposite ends of something, but the mathematics are related. In both of these cases, what we're able to prove is that the Nusselt number is less than or equal to an absolute constant times Rayleigh to the 1/2. Now, this is what I consider to be a maximally unsatisfying result, because we got a mathematical result which has the Prandtl number dependence of this theory, but the Rayleigh number dependence of this theory, right? And the only thing that it does, it doesn't rule out, certainly doesn't rule out this theory at all, but what it does do is it rules out this theory at high Prandtl number. This theory cannot be correct at high Prandtl number. And in fact, at high Prandtl number, if you take the Prandtl number to infinity and you change the equations a bit, then in 2006, so just 10 years ago, Felix Otto and Maria Resnikoff and I were able to apply this background method and actually prove that Nusselt number is less than Rayleigh to the 1/3 with some logarithms there. So the theorems, as of 10 years ago, were that this theory is probably correct at high Prandtl number, but it doesn't say what's going on here at low Prandtl number. But then things changed 5 years ago. My former student Jared Whitehead and I published a paper where we actually went back to Rayleigh's original model, 2 dimensions and 2 spatial dimensions and stress-free boundary conditions, and applied this background method. And in that case, we were able to prove analytically that the Nusselt number is less than or equal to Rayleigh to the 5/12 asymptotically as Rayleigh goes to infinity. Now, I'm just going to complain that physical review letters would not allow us to cite Lord Rayleigh as Lord Rayleigh. They insisted that we call him L. Rayleigh, like his name was Larry Rayleigh or Lawrence Rayleigh or something. Leonard Rayleigh, I don't know. Who's that guy? Anyway, I like to complain about that. Anyway, so we have this theorem. Now, the interesting thing about that is, well, you can do this calculation in your head as well. 5/12 is less than 6/12, which is a half. So that says that this theory it cannot possibly be right, at least under those conditions, so that the physical argument that led to this kind of scaling is not true in general there. So this is one of those situations in nonlinear high turbulent fluid dynamics where theorems have actually informed theory, which is nice and valuable. So I would just like to end with saying admitting to you, my name is Charlie, and I have an obsession with convection. I think it is the most important and the most complex force of nature, and it determines the world around us to an extent that it's really hard to fully appreciate. And with that, I will thank you for your attention.
Thanks, Charlie, for this wonderful survey and talk. We can take some questions. So I have to pass the microphone, maybe myself. Okay.
That was really a great talk, and I think we all really enjoyed it. I'm not sure this thing is working. There. Okay. Okay. So my question, I have actually a lot of questions, but I'm just going to ask one, and it is. It's not clear to me exactly what the relationship is between the onset of instability in the scaled numbers that you showed, the log-log plot. So the instability in convection versus turbulence. I mean, turbulence is normally when you consider turbulence, and you don't know anything about convection, but you consider turbulence, you have an onset for turbulence, and you consider Reynolds numbers.
Right.
And so, which is also a kind of, you have laminar flow, and you have the breakdown of laminar flow, which looked reminiscent of what you were talking about.
So there is a Reynolds number emerges out of this. I didn't bother with that. It's also interesting to know what is the Reynolds number as a function of Rayleigh number. The control parameter here is the Rayleigh number. The Reynolds number is an emergent quantity there. And as I say, that's interesting. That would just talk about the intensity of the flow. That's a measure of the intensity of the flow, which is not unrelated to the heat transfer. So they're related, and so on. But the onset, the physics of the onset is extremely different from the physics of the turbulence. There's no question about that. The remarkable thing from the mathematical analysis is that you can use mathematical methods of stability theory, and I didn't tell you how, okay, but those, the idea of the spectrum of operators is important in the turbulent regime. It's not for the same reason. It's not because you've done perturbation theory. There's no perturbation theory. It's fully nonlinear, fully finite amplitude stuff, but it's neat that the mathematical technology transfers. So the turbulent dynamics is very, very different. I glossed over all of the beautiful details. And there is a Reynolds number, but it's emergent. It's not specified here.
Is there a sharp onset for turbulence, just as there's the sharp onset?
No. There's a sequence of bifurcations. There's a sequence of period doubling bifurcations. You go from period doubling to chaos. Then you have spatial temporal chaos, and then you start shedding plumes. It's very complicated.
Okay.
Yeah.
Good.
We have another question here.
My memory is that Raleigh made an incorrect prediction about the temperature in the interior of the Earth, and that you also have to take into account the fact that these materials have radioactive decay in them.
That's right. In fact, it wasn't until I think the 50s and the 60s that people understood the fact that 80% of the heating in the mantle is due to radioactive decay. He assumed it was all primordial basal heating there. That's right. And also the cooling rate of the Earth is very much determined by convection through the mantle.
This is when he was talking about estimating the age of Earth. So
The age of the Earth. They want to, given that it was molten metal at T equals 0.
Okay, Saber.
Well, this is a mathematical question, not
Sure.
physics. I mean,
Okay.
all these questions were from physicists, so
It's
let's
okay.
just change it to.
So I'll put on my math hat.
Okay.
Okay.
Now you mentioned Ed Lawrence and
Yeah.
his three differential equation
Yes.
system, three-dimensional system, and chaos theory.
Yep.
And then you mentioned turbulence.
Right.
Now, most of mathematicians will only talk about chaos. And is there any?
No,
is it the
some of
same
us.
thing?
Excuse me. The fellow sitting next to you on your
Yeah.
left
Yeah.
is a mathematician who talks about turbulence as well.
Well, I'm from dynamical system theory.
Okay,
He's
yes,
from
right,
PD,
right.
so
Yeah.
that's a big difference. So, is it the same? That's my question.
Okay. Turbulence, if you like, is extremely high-dimensional chaos. I mean, it's still deterministic. Turbulence, as we understand it, unless there are singularities in the equations that have, spontaneous stochasticity introduced, which I'm not admitting that. Even for smooth solutions of these PDEs, you can still have those complicated. That movie I showed, that was direct numerical simulation of the equations, fully resolved.
Okay.
Right? Now that's chaos, but that's chaos on steroids, right? That's not just one or two positive Lyapunov exponents, right? That's extremely chaotic, high-dimensional chaos. The attractor is very high-dimensional in this case.
So, but chaos is in general is defined on metric spaces even. So it's just very high. Any dimension actually. There's no specific
so
dimension.
chaos means sensitive dependence on initial conditions, right? And it certainly, which then in our experience means you get this very complicated dynamics and very unpredictable dynamics, effectively unpredictable dynamics. And it certainly exhibits that. But it also exhibits scaling, statistical features, and so on. Yeah.
Okay, next question.
If I understand well, your last theorem was based on the Rayleigh's conditions.
Yes, correct.
Okay? So does it rule out also the law in the actual materials?
Right. So those physical arguments, the physical argument for the 1/3 exponent and for the 1/2 exponent, those physical arguments and the scaling arguments that go into them do not depend upon the boundary conditions. So our theorem doesn't rule out those exponents, but it says whatever argument you're going to give for those exponents had better invoke the boundary conditions. So it could be that they're correct, but not for the reasons people think they're correct. There. So it's an open problem, and I invite all of you to please come and share my obsession with convection. This is 100 years later, and we still don't really know what's going on at high Rayleigh number. Here.
Okay.
Thanks for the very inspiring and educational lecture. Regarding the density variation, you see that you neglect. What I understand, if we take the density and made an asymptotic expansion, the whole model is in the leading order of the constant density.
That's right. That's the Boussinesq approximation.
As
Yeah.
we see, it's very sensitive, how damages neglecting
yeah,
the correction
yeah.
density variations
Yeah.
due to the whole sensitive analysis.
Okay, so the belief is that those higher order corrections, even in the turbulent regime, are still going to be higher order corrections. That the dominant dynamical mechanisms are going to be what we see in this model. There are no theorems about that. In fact, we don't even know that in 3 dimensions that these equations of motion don't have finite time singularities. This is 3-dimensional Navier-Stokes is inside this system there. So, there are assumptions there, but there are the density variations. The experimentalists are very careful to keep density variations to about 10%, which earlier at 1%. Very small amounts. And there have been benchmark tests and confirmation with numerical simulations, not at the highest end because numerics can't get there. I should have said that the Rayleigh number in the can that you saw was about 10 to the 9th, but we want to be at 10 to the 15th, 10 to the 20th. So we're still orders of magnitude away from where computer simulations can confirm experiments, confirm or deny experiments.
Okay, one more question.
As or can we say the temperature, the total temperature of Earth increases or decreases according to you say? Temperature of Earth increases or decreases?
Oh, you mean global warming? You mean the climate, climate
yes.
stuff.
Yes.
This theory, this component would be one tiny piece of a climate model. A climate model has to take into account where the Earth is being heated at the equator, it's being cooled at the poles, and the oceans and the atmospheres are carrying the heat from one to the other, and there are salinities, and there's moisture, and there are clouds, and there's albedos, and this would be one little piece that goes into those gigantic models that make the big pictures of the Earth. So resolving this would give us a better climate model, resolving this issue. Okay, but it in itself is not going to. Now, do I believe in global warming? I think the evidence. I'm convinced by the evidence personally, but it not not because of this. Yeah.
Okay, well, I think we exhausted the audience. Thank you very much, Charlie, for a wonderful talk. There are a couple of announcements before we move on. The first announcement is that the organizers would like to ask those who would like to publish their full article to be published in the Arab American University Journal, which is this journal of this university. So you can talk to some of the locals about the submissions, or maybe you're going to get an email maybe later from the local organizers about this thing. The second announcement, which is very important, because tomorrow many people would leave immediately after the end of the conference. We have agreed to have the business meeting today at 6:30 in the hall where we're holding the math section, which is in the same building there next door where we go, and at 6:30. So it's open for public. We're going to discuss a couple of things, including where we're going to have the next meeting. Thank you very much again, Charlie, and let's probably move quickly to the next buildings in order to catch up with the time. Thank you.
Of quantum dots, they're not quantum mechanically similar. I mean, they're not quantum mechanically identical, which means that there's always some variation in
Yes.
these transitions, right?
Yeah, actually, this is the main problem in the quantum dot lasers.
Yeah.
Previously when they were expected that the quantum dot lasers will be very different from other lasers, but because we can't have a single quantum dot, this is a problem.
Yeah.
And in the graph technique, we get very different quantum dots.
That's right.
And you are dealing with a complex system. But if we can have a single quantum dot laser, there will be a new important story about lasers, quantum dot lasers. But this is up to now, up to my knowledge, it's not possible at all.
It's really single. Okay, thank you.
Thanks. Okay, Dr. Zaki Saleh from Arab American University. He's talking about advanced plasmonic interfaces for enhanced light trapping for photovoltaics.
Good morning, everyone. This work is done. Let me read the title: Advanced Plasmonic Interfaces for Enhanced Light Trapping and Photovoltaics. This work was done in collaboration with a group at Middle East Technical University, a center called GUNAM, which is basically the abbreviation for Solar Energy Institute. The collaborators are Hisham Nasser, Inkin Skol, Arban Dek, and Rashid Karami. The outline of the talk is the motivation, introduction, samples and experiment, results and conclusions. Okay. Motivation, although despite the falling prices of oil, renewable energy is still a very great challenge for the world today, for this century. Solar energy is abundant and clean, and represents the most competitive competition to fossil fuel. Now we have two types of solar energy, solar cells or photovoltaic devices. One is based on crystalline silicon, which we call bulk materials. These are efficient, but they're very expensive and they're not competitive yet, except for high-tech applications such as space applications. Thin film devices, which are easy to produce, much easier to produce and lower cost, have less efficiency and also they suffer from what we call metastability. The devices are not very stable. Thin film devices do not, one of the problems of these devices are they do not harness all of sunlight. Approximately 15% to 20% of the visible spectrum only is absorbed by these devices. Light management schemes such as surface texturing, anti-reflective coating, and up and down conversion are used, but they have limited enhancements. Plasmonic interfaces, which are described today, are promising, but some issues remain. I will tackle the two important issues of the position and distance from the observer or the device in this presentation. What are plasmonic interfaces? Basically, they consist of metal nanoparticles such as gold or silver. We use silver because it's cheaper, and they're integrated or deposited on the amorphous silicon or the device itself, or basically the device is deposited on them. So that we have two configurations, one of them on the back integration or the front integration. The back integration we deposit on the substrate. We place the nanoparticles, these here, and then we put a spacer layer to adjust the distance between the absorber layer and these nanoparticles, and then we put the absorber layer, which could be a device or just a film, to avoid device complications. We use enhancement in the photocurrent instead of a device just to avoid device complications, so that the enhancement we obtain is not obscured by some device manufacturing errors. So we use this we use amorphous silicon 150 nanometer on top of these, and the other configuration will be the opposite. So the nanoparticles are deposited on top of the amorphous silicon. Okay, now what is plasmonic resonance? Okay, a plasmon, you all know, is plasmon is basically the quantum oscillation or the oscillations of plasma. Okay, plasma oscillations, which the collective frequencies of the plasma, of oscillations of the electrons in a plasma. A plasma consists of a mobile charge at resonance, a photocurrent may be enhanced by two mechanisms. One of them, at resonance, the electric field near the interface, near the nanoparticle, which is close to the interface, is greatly enhanced, and that would increase the movement of the electrons or the charge carriers. And the second is a preferential scattering of the light that is scattered by the nanoparticles. So interface scatters light, and this scattered light can be channeled by appropriate use of refractive indices to be directed toward the solar device, so we can enhance absorption in the device. Scattering strongly depends on the size and shape. We can scattering by the interface, so it will be absorbed by the device. So this is basically what we need to do. And scattering strongly depends on the size and shape of the nanoparticle. The nanoparticle at about 100 nanometer produces the best round shape nanoparticles, produce the best scattering. Okay, there are theoretical calculations by this reference, is not here, I'll show it in a minute, by this reference by Catchpole, predict that the cross-section, the scattering cross-section increases while the preferential scattering decreases as you go away from the device. So as you increase the spacer layer, which is the distance of the interface to the device, the cross-section, scattering cross-section, which we want, increases, and but the scattering, the preferential scattering, the portion of the light that goes into the device decreases as you go away. So the photocurrent enhancement is basically a trade-off between scattering, cross-section, and preferential scattering. So you have to maximize those two and get the best photocurrent. This is the reference for those interested, but it's gone. Okay. Our samples are silver nanoparticles prepared by de-wetting. The de-wetting process is basically you deposit a continuous film of 15 nanometer of silver, and then you heat it in environment, in inert environment, which will make it dissociate and form spheres, which are on the nanoparticle scale. These are the three configurations we have. We have the back configuration, in which the nanoparticles are opposite to the shining surface, the incident light. So in the back, here it's on the front, and here we tried also double, both cases. Okay. This is the de-wetting technique. So we have two samples. Okay, we have one de-wetted at 220C, and the second is at 420C. Although 220C is commonly used by people in this research, we show that de-wetting is not really complete. If you look at this sphere, this is SEM photo of the film, of the silver film on glass. So the nanoparticles are not spherical, and also there are many small nanoparticles. The distribution looks like it has two humps here, so it's not even uniform shape. In the 420C de-wetting, annealing, you have a good distribution, and all of the particles are about 100 to 120, which should maximize scattering. Okay, and we remember we want scattering to be large, so we can divert it or redirect it into the device. This is the transmittance minimum. So at 220C it's small and broad, while at 400C it's very more prominent. Okay. Before we study various configurations, something is missed by many researchers, is that the de-wetting mechanism depends on the substrate. So if you put nanoparticles on the back, which is on glass, while if you put it on the front, it's on silicon, or it's on silicon nitride. And this makes many changes. So if you deposit on if you do the de-wetting on glass, you get spherical particles, like I showed before. But if you put it on amorphous silicon, it's clearly not very spherical, and there are different sizes. If you go to silicon nitride, which is actually what we need for the front integration, it's probably better than this, but not as good as that. Okay, So this is our front configuration, this is our back configuration. We rarely need to deposit nanoparticles on silicon itself. Transmittance. Silicon nitride, we have silicon nitride spacers, redshift and broaden. This is what we notice for both temperature. If you increase the thickness of the spacer layer, it redshifts. It means go to higher wavelength, and as you increase the thickness of the spacer layer at both temperatures. Again, the dip in the transmittance is more prominent at the higher temperature because the nanoparticles are more spherical and more uniform. Okay. This is the various temperature instead of thickness. So again, at higher temperature, we saw at the spacer layer thickness. This is a repeat of the first one. Anyway, so this is the film without any spacer layer, zero spacer layer, here 0, and then at 30 nanometers spacer layer. This is the silicon nitride, what we use between the nanoparticles and the absorber layer, the amorphous silicon film. And this is the red dot ones are at 60 nanometer silicon nitride. So I want to stress this point. Instead of using, although the transmittance is very clean and nicer curves, it's not actually a good representation of how we handle this thing, okay? Because light enters a sample, it is either scattered at the surface, back reflected, or transmitted. We can measure transmitted light, we can measure reflected light, but we don't know what happens inside the combined structure of amorphous silicon and the interface itself, the metal nanoparticles, okay? So instead we use what we call extinction. Extinction means light that's neither reflected nor transmitted. It's not measured either way, it's lost in the sample. When it's lost in the sample means it's either scattered somewhere away from our detector, or it's absorbed by the interface, by the silver nanoparticles. What's lost by the silver nanoparticles is not good. That's lost. It's called parasitic losses. What the portion of light that's scattered is actually, we have the ability by choosing the appropriate refractive indices of the two combined structure to divert it and channel it into the device, as I said before. So in general, what we have here at 220C, we have more extinction at this is 600 nanometer is about the band gap, corresponds to the band gap structure of amorphous silicon. So this is basically the band gap. So near the band gap edge, okay, we have more extinction. More extinction means there's more light that's either absorbed or scattered. We cannot tell at this point whether it's absorbed by the silicon or not. All we know, it's lost light in the structure, okay? It's not transmitted or it's not reflected. We have more so at the 420C. So this is the comparison between the two cases. But the good point is all three interfaces have good extinction at about the edge of the band gap, where most of the light is actually lost because wavelengths with energy light with energy less than the band gap is usually not absorbed well, okay? We need to look at this curve. It's too crowded, I'm sorry for this, but I must present it in one slide so we can compare things. We look at the photocurrent now. Photocurrent in amorphous silicon, which is a representation of light that is absorbed by the amorphous silicon, which means it was scattered by the nanoparticles. It's not absorbed by the interface, it's scattered by the interface and absorbed by the amorphous silicon, which involves scattering, cross-section enhancement, and scattering diversion into the amorphous silicon, what we call preferential scattering, okay? If you look at the first, the results of the no spacer layer, which is here, this is zero photocurrent. There's no enhancement in the photocurrent with zero zero spacer layer. Zero spacer layer means we don't have any insulation between the nanoparticles, which is metal, and the semiconductor, which is the amorphous silicon. And that usually is not a good combination, because nanoparticles may act as recombination center and kill the photocurrent, but also at the same time they may enhance the photocurrent by changing the current path. This is a very good point, because the editor of this gave me a hard time when we first published it, but we finally made a model to convince them how this might work. So the photocurrent enhancement for no spacer layer could be zero, but here it could be very large. So it's completely unpredictable. And with the model we proposed and published in this paper, it's actually very well explained, okay? Because the nanoparticles may act as recombination center and kill the photocurrent, or they may shrink or reduce the conduction path and enhance the photocurrent. Therefore, we conclude that these data should be excluded. But we go to a higher spacer layer. Here we have 60 nanometer and 30 nanometer. The 30 nanometer has much great enhancement of a factor of 3 in photocurrent, which means we are able to successfully scatter light by enhancing the scattering cross-section, and we were able to select the appropriate refractive indices, because for silicon the refractive index is about 4, and for silicon nitride, which is the spacer layer, the refractive index is about 1.5, which we all know from elementary light that the light will be scattered closer to the normal, which will go to the amorphous silicon layer in this configuration. So it's basically lucky that we have a higher refractive index silicon compared to lower refractive index silicon nitride. So we have a factor of 3.5 enhancement in photocurrent, okay? And at lower temperature de-wetting, this is 220 C, we have about 1. This still is a good enhancement for photocurrent in a silicon device, in a amorphous silicon device. How much time I have? What I presented there was maybe I didn't stress that point. What we presented in the previous slide was the back integration, where the nanoparticles were deposited at the back of the surface opposite where the light is shown from. Okay. In this case, the front integration, the photocurrents are less enhanced. So we look for the 10 nanometer here. We couldn't get the 60. We saw it was too large. For 30 nanometer, the enhancement is less than 1. Okay. While at 220 C, it's a bit about 2.5. As I said before, the nanoparticles produced at the silicon nitride are not as good as I showed you in the images. So the enhancement here is not as good for the rear integration. We also tried the third case, double integration, where we have nanoparticles at the back of the sample and at the front of the sample. I don't know if I wrote here. Yeah, it's 10 on the front and 30 nanometer on the back. And the enhancement, this is the amorphous silicon without any interface, and the enhancement is good. But we attribute this enhancement basically to the interface on the back, because the interface on the front actually has a problem inherently in it, because it's at the surface where the light is coming from, okay, and it will shield some of the light from going to the device, and there's some losses there, while at the back we'll handle only the light that's also already lost. If you think about the light that's going into the device, okay, instead of dealing with it at the front surface before it goes into the device, no, we wait until the device absorbs as much as it can from it, and then what's transmitted, the 10-20% from it transmitted, because we handle that and trap it and get it back into the sample. We tried also, because we want to harness all light that's near the band gap energy of the device. We tried something that's really unique. We tried 2 different interfaces on top of each other. Okay, successful. So with the samples here, you see the upper layer and the lower layer. So we're able to successfully produce a stack of plasmonic interfaces of silver nanoparticles with very small layer, insulating layer between them, so they don't interact with each other. And we were able to produce an extinction. The red is the extinction spectrum. Okay, that's broader, so we can get more light absorbed by the device at a different frequency, different energy. Okay. Okay, so this is my conclusion. The photocurrent in amorphous silicon is used as an indicator of light trapping by the plasmonic interface, and we are in the process of actually transforming this data into a device. Okay, so we're building now device, plasmonic interface on devices to see the enhancement in a real device. Photocurrent enhancement in the 600 to 700 nanometer range, okay, is consistent with the redshift in the extinction spectrum. So we get extinction spectrum in the 600 to 700 nanometer range of the incident light, and that's exactly where we get the enhancement in photocurrent. Integrating plasmonic interfaces to the back surface seems to be the best on the back, as explained this before, because that light will be already lost. So if we channel it back to the device, it will be a total enhancement. While in the front, it may actually block some of the light from entering the device, and the process cancel any enhancement due to the plasmonic interface. I can't read. The spatial layer serves as, this is a good point. The spatial layer doesn't only adjust the surface, the distance between the plasmonic interface and the device, it also passivate the amorphous silicon from interaction with the metal nanoparticles. If you deposit metal on a semiconductor, you never know what happens from the surface of this nanoparticle. You could have trapping of light of carriers, so trapping of carriers and recombination, and this will actually reduce the photocurrent. Optimum enhancement in light trapping is the trade-off between, this is a confirmation to the theoretical predictions by Catchpole in the reference I showed before. The optimum enhancement in light trapping is the trade-off between scattering cross-section and which increases the differential scattering and decreases with the spacer layer thickness. Okay, and thank you for your attention.
Thanks, Dr. Zaki, for your talk. Have questions? Just take 2 questions.
Thank you, Dr. Zaki. I wish really to know if you have measured the JV plots, because saying photocurrent means current at zero applied potential. Current density versus potential. Did you do this measurement?
No, because the sample has the same cross section. We have the same identical device structure. The enhancement in photocurrent is the enhancement in the photocurrent density. Unless I didn't understand you.
Not necessarily. No, I'm not talking the difference. I'm not talking about density. Sorry. I'm talking about if you are using potential in your measurement or not. Exactly.
Of course,
have
our photocurrent measurement is basically with the 2 coplanar electrodes. I hope I am understand your question. With coplanar electrodes with identical gap between the 2, and we apply a voltage from 0 to 10 volts, and then we get a slope, and the slope gives us the conductivity and the photocurrent.
So at 0 potential, you have seen photocurrent? That's
no, 0. We don't see photocurrent.
So it's not photocurrent then.
Okay. No. No. It's we at 0 potential we apply a current, okay, and we subtract the dark current. So actually we see a photocurrent. No. Yes, the IV characteristics, the IV curves. I don't have it here, but I can show it to you. But what we do is we do an IV under light. This is how the photocurrent is calculated, and subtract the dark. Okay, I'll be happy to send them to you. Yeah.
You can ask. Well, Dr. Saleh, discuss it.
But all of them are done that way. We did we didn't take one point.
Second question.
I was
But before you continue, I talked about two kinds of double layer. One of them, two double layers next to each other as single interface, okay, which I presented the last thing, and we have double interlayer, double interface, one at the front of the device, one at the back of the device. Which one you're talking about now?
Well, it's my question really just relates to
Yes.
with the best results that you've obtained.
Yes.
Okay. How does that compare to the efficiency of the conversion of light to useful electric current? How does that compare to a bulk single crystal silicon photocells? First of all, in the performance, efficiency in the scientific performance, and then how does that relate to the cost, the overall cost ratio? That is to say, even if your efficiency might be a little less, if the cost is a lot less, then the price to performance might actually still be favorable. So that's my question.
Yeah, thank you. Okay, the first part of the question, basically, it's not costly. It's really not costly. It's just you deposit the piece of evaporate film, silver film, 15 nanometer takes minutes or seconds, and then you put it in the oven for half an hour. That's all what it does. Now, the thermal budget of this process is a big concern because my data shows you must go to 400. And 400, if you put it on top of the device, is a problem because silicon may change under that temperature. Remind the second question is if the total enhancement, we tried it on a device and the device had a problem that we built. The device takes time to build. There are several things and several errors may occur. It was shorted out, the device. So we're doing that right now to compare how this enhancement is transformed into a device. And this is the ultimate test, of course. All this work is not meaningful in a sense unless you prove it in a device. Thank you.
Okay. Thanks again, Dr. Zaki, for your talk. Okay, let me ask the third invited speaker, Dr. Ulrich Eckern from the University of Wolfsburg, Germany. He will talk about transport properties of spin-orbit coupled Fermi systems.
Okay, good morning everybody. It's a great pleasure to be here again, and I would like to thank the organizers for inviting me. You have a wonderful country and it's always good to be here. Today I would like to talk a little bit about transport properties of spin-orbit coupled Fermi systems. So the model I'm having in mind is a layered system, and for the purpose of this talk you can simply think of a two-dimensional electron gas with some small corrections. Let me first, I will come back to this picture a little bit later. Which is the one? This one, okay. These are the people I have been working with. Sebastian Döller is my doctoral student. Cosimo Gorini was my doctoral student about 5 years ago. And Roberto Raimondi is an old friend from Roma 3. Roberto, some of you may remember, he was also visiting, I think, the first and the second conference of this series. And I'm referring especially to these two papers which were published a year ago and 2 years ago. So just, not everybody may know where the Augsburg is. So in a way, if you look at this picture, it's in the heart of Europe, so to speak. So here is Augsburg, and some people say it's near Munich. This is fine. We say Munich is near Augsburg, but okay, never mind. So you get a rough idea. It's a rather old city. The university has about 20,000 students, mostly in humanities, law, and in economy. Physics was founded not so long ago. And we're having mostly condensed matter physics. It's about 24, 25 professors and about 700 students in physics and material science. I brought some information. We have new brochures, so if somebody is interested coming to Augsburg, please have a look. Okay, here's a brief overview of my talk. The essential thing is I will give you, so to speak, a two-part introduction, and this is the most important for you. So to get an idea what I'm talking about. Then in between there are occasionally some slides which are a bit technical, and I will not go into great detail. So this concerns this part here, the Boltzmann equation. But some of you have seen a Boltzmann equation, and this is a slight generalization of the usual Boltzmann equation. And then I will discuss a little bit about spin thermoelectric effects and phonon skew scattering, which actually is a pretty old business. Skew scattering goes back to Mott 1929. I will give you the reference a little bit later. So what am I talking about? Just to give you a few buzzwords. This is a Hall effect that everybody knows. Two-dimensional electron gas, perpendicular magnetic field, and so on. There's also an anomalous Hall effect when you have a magnetic system. And there's a spin Hall effect. And the spin Hall effect, and this is an experimental result. By the way, this is mostly theoretical. I'm only referring occasionally to some experiment. So the spin Hall effect, you drive a charge current in this direction, and you find that there is a spin or magnetization, say, up here and down here. I think this is an optical measurement. So there's a finite spin density. So what happens, due to the coupling between charge and spin, when you have a charge current here, the spin goes perpendicular, and you can measure it here, as in this experiment. This is a well-known experiment. And when you have such an effect, there's also the inverse of the effect and the spin-Nernst effect. I will come back to that a little bit later. Something which is called Edelstein effect or spin galvanic effects. I mean, all this is related to the coupling of charge and spin and applying an electric field or a temperature gradient. I have a few more pictures, so really to impress this upon you, what I'm talking about. So again, now this is it's nice and green, but sometimes it's not working. Let me try. Okay, good. Back to the mechanics. Okay, so here the first one, the Hall effect, once more. Electric field, magnetic field perpendicular, then there's a Hall current or Hall voltage. It's okay. It's okay. You can move. Okay, the other one here, the Nernst effect. It goes back to 1886. You have a same sample, two-dimensional electron or hole gas. You apply temperature gradient. You have a current, maybe electron or hole current, and then you get the Nernst effect perpendicular. Or spin Hall effect, I discussed that already. Charge current this way, and the spins move in different directions. And the spin Nernst effect, this work, of course, this work refers to this work which was published only a few weeks ago. So the spin Nernst effect was only few weeks ago measured, and these people, here you find the references in July on the archive. Even once more, slightly different arrangement of figures. I said this is the most important part of the talk. Again, the Hall effect, the anomalous Hall effect in the presence of some, if you have a magnetic material, have some magnetization, and here again the spin Hall effect, you have the charge current, one spin direction goes this way, the other spin direction goes the other way. Another very important experiment experimentally is what is called spin pumping. Again, you have an interface here. Here you have a magnetic material. I think permalloy is used quite often. There you have a magnetization, On this side, you drive the magnetization, and due to the spin-orbit coupling near the interface, you generate a spin current in the normal metal. So and the spin current, actually in the normal metal, you can measure then by the inverse spin Hall effect. You have a spin current which generates an electric field perpendicular. This is the inverse spin Hall effect. I mean, all these things are done experimentally, not by me. This is a very flourishing field. It's I think for about 10 or 15 or 20 years. A lot of experimentalists involved, and this field, I find it exciting. Good. And to show it to you once more, the quantities I want to calculate or discuss a little bit later. Say, okay, again, the spin Hall effect. Here you define the spin Hall conductivity as being the proportionality factor between Ex, the field in X direction, and the current, the spin current in Y direction, polarized in that direction. You have to, I know it's difficult. So this always refers to the spatial direction, and this refers to the spin direction. This Z component is up, down, so to speak. So, and this, I mean, the picture, of course, here it's clear. So, actually, this goes back to Diakounov and Pirel, and it was observed in 2004, and I showed you the picture a few minutes ago. The analog is very clear. These are the simplest effects. I talk about the theory a little bit later. Spin-Ernst effect is the same situation, but you apply a temperature gradient. And you find a separation of spin. Now, temperature gradients in nanostructures or in very small systems, of course, are very difficult to measure and to realize. So, as I said before, this was seen only recently in experiments. Now, what is at the heart of all these considerations? I said it before, it's this coupling between spin and charge, and spin current and charge current. And what is important for that is the spin-orbit coupling, of course. Now, the interesting point is, this is the standard form of spin-orbit coupling, which you learn, I don't know, in quantum mechanics, 1 or 2, I'm not sure. You have the sigma is the vector of Pauli matrix, there's a gradient of the potential. It's a multiplied scalar product with the momentum, and then there's a factor in front, minus lambda squared over 4h. And this lambda squared, this is the important thing when you have a solid state system because of all the band structure effects. The solid is complicated. There are many bands. You have to somehow downfold the bands to get an effective Hamiltonian. And when you do all that, and people know how to do this for 50 years, when you do all that, you find that the prefactor here, this lambda, the Compton wavelength, so to speak, is now an effective Compton wavelength, and it's by a factor 10 to the 3 larger than in vacuum. That is why all these effects in solid-state systems are observable. Otherwise, spin-orbit coupling is very, very small. Now, in this field, people distinguish actually 2 types of spin-orbit coupling. I mean, this is a general form, but then when you go on a little bit, one is due to the bands or the structure of the devices. You usually talk about layered system. And of course, there is a structure inversion asymmetry. And under such conditions, you get what they call intrinsic spin-orbit coupling. And this intrinsic spin-orbit coupling is connected, for example, with the names of Rashba, and was studied also by Diakounov and Pirel, and there are some characteristic relaxation rates to which I come back a little bit later. The other one, what you also have usually, there are some defects in the system, some imperfections, whatever. And this is called extrinsic spin-orbit coupling. extrinsic spin-orbit coupling is associated with the name, I mean the relaxation is Elliott and Jaffet. So these are the important ingredients of a theory. This is not important. So we have to model the system. I said it's essentially a two-dimensional electron gas. So it's very simple. If you put everything together, first you have the kinetic energy in the Hamiltonian, then you have this Rashbach kind of coupling I discussed before. This Rashbach kind of coupling is very simple in a way. It contains sigma cross z. Z is a unit vector in the z direction perpendicular to the layers, multiplied by p, and then there's a prefactor which is usually called alpha. Second, there is impurities. Impurity have some potential, and what you do in a very simple model, you model it as a random potential. So the electrons move through the crystal, and it's occasionally scattered, so this is impurity potential. And then comes this additional effect through the spin-orbit coupling, where you have this lambda squared in front, and here you have now the gradient of the impurity potential. And these are the interesting terms. This term and these terms are the interesting. To give you an idea, this extrinsic spin-orbit coupling to the impurities, that's this one. There are two contributions. They're called side jumps and Elliott-Jaffet relaxation. For example, Elliott-Jaffet relaxation. And the main part of our work was essentially, and this is, so to speak, to summarize it very briefly, to consider what happens if you look at finite temperatures, when you have, instead of impurity scattering, electron-phonon scattering. After all, many of these experiments are done at room temperature. You have to take into account the temperature dependence of the scattering rate. And maybe some of you worked on electron-phonon scattering, you know this can become quite difficult. But it's important from an experimental point of view, and this is the main part of our work and of the two references I showed you before. Okay, these are just some hints what is been done. And this only to flash you. I told you all these calculations are done on a quasi-classical level. That means you look at a Boltzmann type of equation, and the idea is that electrons essentially are wave packets moving around, moving diffusively, and this can be described by a Boltzmann equation, and then it's getting a little bit involved. I don't want to get into details, but the Boltzmann equation is written here. Well, there's also this old joke. What is the form of the Boltzmann equation? Left-hand side equals right-hand side, right? So this is always the form of the Boltzmann equation. Now, there's a distinction usually. Here's a time derivative, then there is a divergence of a current usually, and here comes a force, and on the right-hand side you write the collisions. I mean, that's the way of doing it. And here are the standard collisions and the side-jumped Elliott-Jaffet, and the central point here, all this, because we talk about the coupling of charge and spin, all this is done for a distribution function which contains a charge sector and a spin sector. We want to describe this coupling between charge and spin. So actually this F is a 4x4 matrix, and so it's getting quite involved. And the other things are not so important. Essentially, it's a gauge invariant generalization for people who like the old-fashioned diagrams working with Green's functions and self-energies. I'm just showing these here. This is a standard self-energy diagram for collision. Here you have one spin-orbit insertion. Here you have two spin-orbit insertion, and this has to be generalized for finite temperatures. Also, very briefly, I'm still talking on the level of the model. This is the typical modeling of impurity scattering. You say you have you have a random impurity potential, and it's delta correlated. The interesting thing is when you generalize this to finite temperature, and look at high temperature, you can treat phonons in the same way. Phonons at high temperature, the scattering of electrons at phonons is quasi-elastic. So at high temperatures, phonon scattering is very similar to scattering at impurities. The only difference is that scattering rate due to impurities has to be replaced by the scattering due to phonons, which is proportional to the temperature. Just as a note, I did not use this here, and this prefactor usually is also called lambda, but of course I try to avoid it here. And this is the lambda which determines the critical temperature of superconductors, and it also determines the mass enhancement of electrons coupled to phonons. Okay. How much time do I have? 5 minutes? 2 minutes. Okay. Okay, so we have gone through all this, and this shows you briefly the form of the collision operators, and then for the collision operators, once you have solved the Boltzmann equation, you can calculate the charge current and calculate the spin current, and there are some interesting relations, and we have all done this in the linearized regime, and then computed the transport coefficient, which are given here. For example, the spin polarized in the y direction as it's a prefactor, electric field in x direction, gradient in t direction, and these coefficients all can be calculated within the theory within some approximation, and this is actually what is called the Edelstein effect, the connection between spin density and electric field. This is what people call Edelstein effect, and there are some details. There's a summary 1. I have a summary 2 also, but this summary 1, I've told you most of that. So let me conclude with a brief discussion of what I introduced at the beginning, what is called skew scattering, which I said goes back to Mott in 1929. And this is skew scattering essentially is a spin-dependent scattering. So when you have a potential here and you have an incoming electron, I mean the spin up and the spin down are reflected differently. This is a summary of skew scattering. And you have to go, as you here, you can discuss it in terms of this amplitude. You have to go beyond Born approximation to see this effect. That's also indicated what people call side jump. I mean, spin up electrons jump a little bit to the side, spin down electrons jump a little bit to the other side. That's, so to speak, the illustration for the side jump mechanism. And we have looked at this at finite temperatures. This gives you again some diagram, but here is some prediction. We are discussing that with experimentalists. It's not yet clear whether our prediction is a good one or not. What you do, essentially, you plot, that's what the experimentalists do, you plot the spin Hall conductivity divided by the ordinary conductivity, and then discuss how it may depend on temperature. And when you take everything into account, what we know so far, we know low temperature, I mean, here's the temperature, here's the Debye temperature, here's low temperature, we know a lot. For high temperature, we know a lot. So, okay. So, depending on the parameters, and unfortunately, there are many parameters in this field, it's really hard to tell, but we are predicting right now that there might be a maximum as a function of temperature, a minimum, and then finally a linear increase. We're hoping that experiments are done soon. We are discussing it with experimental groups, but this comes out as this was essentially the result of our recent PRL, essentially this part of regime and this kind of discussion, while it's still preliminary and unpublished, and I hope the measurements will be there soon. And my summary 2 I leave out. Thank you very much for your attention. It was a pleasure.
Thank you, Professor Ecker. Do we have questions?
You see the electron-phonon interaction. This is what we call Polaron. Is this?
It's not as strong. it's not so strong to form a polaron. It's very weak. It's an electron-phonon interaction which leads to BCS superconductivity. In superconductivity, for polaron you need very strong electron-phonon interaction, and here it's perturbatively. It's
Take the second question.
Ulrich, in the Mott-Skew scattering, it looked like from your diagram. Could you go back to that diagram for a second?
Oh, sure.
Just the one that shows the spin up and the spin down scattering across the center. Yeah. So is that simply that the electron spin up sees an attractive potential and the electron spin down sees a repulsive potential?
No, I don't think so. I mean, in the scattering amplitude, when you include spin-orbit scattering, you have two terms, the standard amplitude A, but there's a second one which is P cross P prime, I mean P in, P prime out, times sigma. And when you look at it, I mean, you can compute these A's and B's, and you have to go one beyond Born approximation to see it. And that's what Mott did actually in 1929. I mean, the paper he published, I have it here on my computer, is scattering of electrons at heavy atoms. It's a single particle scattering problem, right? It's nothing.
Yeah, but the way the trajectory, this is a trajectory plot, right?
Yeah.
Yeah, so the trajectory plot looks a lot like the red curve is subject to an attractive potential, and the blue curve is subject, if it's jumping in this way, is subject to less attractive or perhaps repulsive potential. So
I admit it looks that way, yes.
Yeah, but I mean, in when you have collisions between atoms, which are essentially one electron atoms, the position of the spin between those two things decides whether or not the interaction potential is plus or minus. So I was wondering if it was somewhat analogous to that.
If you have a spin-independent potential and compute the scattering, of course, up and down is the same. But here you have the spin-orbit scattering. And the spin-orbit scattering leads to these two scattering amplitudes. And this result, I mean, it's of course exaggerated here in the picture. But this result comes from interference terms of the form A, B star, and B star A. So A, if you just look at A and A squared, it's spin independent. And B squared also is independent. But it's the interference here, which comes from the spin-orbit coupling.
Okay, thank you, Dr. Erlich, for your talk. We will close with Dr. Ahmed Omar from the Arab American University. His talk about effect of sodium-based transparent binders on the optical properties of GASE thin films.
Good morning. Good morning. Today I will talk about the effect of sodium-based transparent binder on the optical properties of gallium selenide thin films. The effect of sodium-based transparent binders on the optical properties of vacuum evaporated gallium selenide thin films is investigated. We measured the reflectivity and transitivity versus the wavelengths, and we calculated the dielectric constants and the relations with the photon energy, and then we calculated the absorption coefficient, and we found that this binder make this thin film optically as an optical windows for gallium selenide thin film. Short introduction. Gallium selenide thin films is important in scientific research and applied sciences due to its distinguished characteristics. Measurements and analysis of the absorption coefficient, refractive index, dielectric constant, and optical conductivity for samples of gallium selenide near the band edge have been reported. Shigetomi and Ilkari concluded that the excess of gallium and selenium atoms in gallium selenide samples cause the indirect band transitions. In this work, we analyzed, modeled, and evaluated optical conductivity parameters of gallium selenide binder thin film. Experimental details. We used a vacuum evaporated system to make the thin film double layer gallium selenide plus the sodium based layer. The evaporation system is VCM 600 physical vapor deposition system at a pressure of 10 to minus 5 millibar. The gallium selenide thickness, which is about 1 micrometer, was controlled and measured using a thickness monitor. The optical transmittance and reflectance were recorded using Evolution 300 spectrophotometer. Results and discussions. In figure 1A and B, we plot the relation between the transitivity and reflectivity versus the wavelength in the wavelength range between about 200 to 1100 nanometer. Okay. In the first figure, we have here transitivity versus the wavelength. We notice that there is a sharp increase in transitivity with respect to the wavelength. Here, the second figure, which represents the reflectivity versus the wavelength, we noticed a slow increase in reflectivity followed by approximately an invariance, local maximum, then a sharp increase in the reflectivity. Also, we noticed that the reflectance is very small compared with the transmittance. Here, this local maxima, interesting, which is near 500 nanometer, corresponding to an energy of about 2.48 electron volt, which is due to excitonic transitions in gallium selenide, which explains the origin of band gap in gallium selenide. Figure 2A and B. Here we plot the absorption coefficient alpha versus the photon energy in the energy range 1.16 to 3 electron volt, and absorption coefficient between 490 centimeter inverse to 853 centimeter inverse. In figure 2, we plot the relation between alpha E squared versus the photon energy, okay, in the same range. In figure A, we notice that the absorption coefficient sharply increased in the range, the mentioned energy, photon energy range. Here, the second figure, which corresponds to tau plots, okay, show the slope of the curve near the band edge. The intersection of the curve clarifies the band gap for the gallium selenide binder interface, which is 1.5 electron volt. Oprah reported that within the exponential edge, the absorption coefficient alpha in the absorption coefficient alpha range, alpha greater than 1, 10, less than 10 to the 4 centimeter inverse, the absorption coefficient is given by this exponential equation, where alpha naught is a constant, E is the energy of the incident photon, and E sub E characterizes the slope of the exponential edge. The following figure 3, represents a plot of ln alpha versus E for alpha less than 1000 centimeter inverse. The slope of the baseline is found to be about 0.306 electron volt inverse. From this slope, we evaluate the value EE, which is about 2.32 electron volts. This value, okay, shows the width of the band tails of the localized states in gallium selenide binder double layer. Okay, so this is the relation between ln alpha and the photon energy. This is the baseline, the black line, okay, which represents the trend line. The slope of the baseline is about 0.3 electron volt inverse. The reciprocal of the slope represents E sub E. Okay. To explore the possible applications of the gallium selenide binder double layer interface, we studied its dielectric properties. So, from previous data, we calculated the real part and imaginary part of the dielectric constant from reflectivity, transmissivity. We calculated the absorption, and then the absorption coefficient alpha, and then the extinction coefficient, which is the imaginary part of the refractive index, which is directly proportional to absorption. Okay, here epsilon r is the imaginary part, and EIM is the imaginary part of the dielectric constant. We used this relation, okay, R here reflectance, and the real part of the refractive index, K is the extinction coefficient, which is the imaginary part of the refractive index. Okay, we rearrange this equation, which becomes a quadratic equation, and we solve it for N, which is the real part of the refractive index. Here we know N, and from here we calculate K, then we compute epsilon R and epsilon IM. Figure 4A and B. Here, in figure 4A, we plot the real part of the dielectric constant versus the frequency of the photon, incident photon versus the frequency. The local maximum here is corresponding to about 600 600 terahertz, which is about 2.48 electron volt. This curve is more important because we can use the data and model this curve later to find the optical conductivity. Okay, to investigate the possible applications of this double layer, we evaluate the conductivity from solicitation, okay, and this is another equation for the optical conductivity. From this relation, we use the measured data to find the optical conductivity of the bilayer. The second equation, we use the second equation, which is formulated by Lorentz, okay, to evaluate the fitting curve. Is the angular frequency, gamma is the damping coefficient, which is 1 over t. Okay, omega e is the width of localized frequency. Cam? Okay, this curve is a plot of the optical conductivity versus the frequency. Here the blue light corresponds to the experimental data, and the red light corresponds to equation 3, belongs to the fitting parameters. The fitting parameters are summarized here in table 1. We notice that we have 2 sets of parameters. We notice that the first set we have is a bit slightly greater than the second. Conclusions, main conclusions. Okay, we notice that the optical features of the bilayer show wide absorbability that extends from 1.5 to about 2.5 electron volt, which is helpful in photovoltaic applications. Second, the dielectric spectra of gallium selenide binder thin film shows enhanced optical conductivity and dielectric values. Third, the scattering time of the gallium selenide binder thin film at femtosecond and plasmonic behavior near 1 gigahertz make it suitable for thin film transistor. Thank you for listening.
Thank you, Dr. Ahmed. Thank you. Do we have a questions?
Thank you very much for your talk. You showed the experimental data on AC photoconductivity. Do you have any? Did you make experimental data on DC conductivity, function of wavelength, function of temperature, and so on?
No, we didn't investigate the effect on of temperature on our data.
Yeah. Other question about the width of the band tail in the gap of amorphous gallium selenide. You showed that it's about 2 electron volt, 2.4 electron volt, and I think this value is very wide, very big value, isn't it?
You mean? You mean this value, yes? You mean this value? Yes. Here, this is related to the band tails of the localized tails in gallium selenide binder double layer. Okay, so it extends. It is considered as interband for this system. It is interband. Maybe there is a mistake. I don't know.
Okay, okay. If you please just.
I'm sorry for disturbance, but I must say that in the truth he is measuring the binder tail state, not the gallium selenide. When the binder band gap is greater than 6 electron volt. So when you set it on the top of gallium selenide and you take the reflectivity, you measure from the surface of the binder. As a result, since gallium selenide is down and its energy band gap is much less than that of the binder will see the gallium selenide as a tail, but the tail is not in gallium selenide. Yes. Okay, thank you very much.
Okay, let us thank our speakers in this session, Dr. Muayyad, Dr. Zaki, and Dr. Erlish, Dr. Ahmed, and thank you. We have a 15 minutes break now. Okay, and then we'll be back to the room. Thank you.
إذا سمحتوا يا جماعة خلينا نبدأ السيشن. We will start the session shortly.
Please be seated. Please be seated. This is an announcement from the organizational committee. I will be the speaker for the next talk, but this is I'm talking now as an organizer. For those who are interested in publishing their work in our journal, please let us know. You don't really have to. You don't really have to publish. But if you are interested, please let us know so that we can. We are gonna pass a list for those to indicate their names, so that we can process your publication. Thank you.
Okay. The title of our talk is Surface Analytical Techniques, Advances and Challenges by Professor Saleh. Okay, so
thank you.
The time for you, so we can start.
Thank
So
you.
we have 20 minutes and 5 minutes for discussion, please.
Thank you. This work was done at the VUB in Belgium in collaboration with the Surface Group at the electrochemical group, which is called SERF at the VUB. Ever since men or man wanted to know, extend their senses beyond what you can see by your own eyes, using a magnifying glass. This is just an extension of what you can see, your senses. So you can see things larger. Man did not stop at this point. Man constructed huge machineries to understand the nature of matter. You see here a picture of the synchrotron that is used to understand the nature of matter, and we've seen this in previous presentations. Man also constructed what is called a super collider or a super hadron collider, which we've seen in the first day. What I will do in this presentation is to see, what is the ultimate in trying to identify the nature of material at the surface, with a particular emphasis in a technology called OJ electron spectroscopy, which is used to identify nanostructures at nanoscale, to identify basically the chemical and physical nature of particles. The issue with analytical techniques has to do with the basic sciences that are needed to understand the analytical technique, but also is important for research and development in various areas of technology. Production activities in the microelectronics industry as an example, but not just in microelectronics industry. Quality control. It's also important for materials engineering, in metallurgical activities, microelectronics and photonics, even archaeology and geology. Okay. Here is a class of material analytical techniques that involve basically an excitation source and the emission of some kind of energy. There are, we can excite what we call a sample. A sample can be anything really. We can shoot ions, electrons, light, X-rays, etc. And as a result, subsequent to exciting the sample, we look at what comes out. Ions may come out, electrons, X-rays, etc. So this process of energy incident, energy coming out emitted, with the analysis of what comes out, relating it with what comes in, we will learn about the nature of this green box. We further can actually do the following. We can scan the incident beam, if it, regardless of what the beam is, ions or electrons, and we can look at the what comes out as a function of coordinates. This way we can have what is called spatial resolution. So we don't look at the entire sample as one entity, rather we can see the lateral distribution or the identity of or the composition of the material as a function of lateral dimension, both in the X and Y direction. There are lots of techniques that where we can get ideas about the topology, metallurgy, like SEM, AFM. There are lots of acronyms in this technology. Scanning tunneling microscopy, surface composition like XPS, AES, time-of-flight SIMS. I'm just, for those who are familiar, I don't expect all of you to be familiar with all of these techniques, but these acronyms just indicate what kind of technologies are available to identify or to characterize the surface. Chemical composition, like in the energy dispersive spectroscopy or wavelength dispersive spectroscopy. And we can also, there are techniques that will look actually underneath the surface, like backscattering spectrometry and secondary ion mass spectroscopy, or SIMS. Here is the technique that I want to look at. I want to look at the OJ electron spectroscopy because it really gives you the ultimate resolution in the lateral direction, and that's because we can use advanced electron optics to precisely shape the electron beam into a very, very small spot size. And we can also, using advanced electronics, advanced ion optics or electron optics, to discriminate against areas that I don't want to be looking at. But let's just understand what is the physics behind the OJ electron spectroscopy. Basically, with the OJ electron spectroscopy, you have an electron beam coming in, exciting the sample by creating a hole in a core level, and then subsequent to the excitation of the atom, we have a two electron process in which an electron goes to fill the hole, and then an OJ electron comes out with a kinetic energy that is dependent on the binding energy of these two levels. Now, here is the point. The kinetic energy here becomes a fingerprint for the material. Every material has different binding energy for its core levels. So the kinetic energy, if I could do electron energy analysis of the kinetic energy of the emitted electrons, I can find out what kind of atom did this emission. And in this picture here, we see what is called the volume that's being analyzed. Here we have a primary electron beam incident on the sample, and we can see that we have secondary electrons coming from this depth, but then we have X-rays coming from much deeper, and this defines actually the surface sensitivity of a certain technique, depending on where you, what energy or what constituent or what is being emitted tells you from what depth is this energy coming out. We notice here that the OJ electrons are coming from the top 4 to 50 angstroms. So the top few layers of the surface, we are only seeing basically the top atomic layers of the surface using this technology. This graph shows what is known as the escape depth. This is basically the same here. We look at the escape depth or the analytical depth here as a function of the kinetic energy of the electrons that are being emitted. And we can basically here we can see that here we see silver. These are two OJ lines. So for example, if I want to see a more surface sensitive line, surface sensitive, I would look at this line of silver. If I want to look deeper into the sample, I will take another line for silver. And this goes for the rest of the elements. But we can see here, say, this is 5 angstroms, basically one layer of the material, one atomic layer of the material. Now, to be able to do that, there are lots of advances that made this kind of technique possible. You had to have a very good vacuum. Basically, we are talking about ultra-high vacuum, 10 to the minus 10 torr. You have to have high throughput sources where you can deliver lots of electrons. Precise electronics, complex detection systems that will synchronize the incident electrons with the electrons that are coming out. Also sample preparation, or also the utilization of digital control. You have to be able to store lots of data very, very fast. So you have to have good computers to be able to do that. Another thing that you need to be able to accomplish this task is you need to have standards, or what we sometimes call digital libraries, to compare, because you cannot really calculate this process precisely. So for you to be able to quantify the signal, you have to resort to standards or to digital libraries that are available. This is how an energy spectrum of the electrons that come out look like. This is a cartoon, really. These are electrons that are elastically scattered off of the surface, where we have an electron beam incident with 2000 electron volts. And these peaks here show different lines, or different OJ lines, each one of which is perhaps due to a certain element, or multiple peaks may be due to just one element. Here is how a state-of-the-art OJ electron electron or scanning OJ electron spectrometer looks like. Where you place the sample here, you have an incident ion beam, and you have a complex energy analysis analyzer, and then a stage that can be manipulated through computers. The ultimate resolution for this system is the ultimate resolution in the lateral direction is 3 nanometers. That is about, well, that is 30 angstroms. Also, we are talking about very, very small structures. Now, remember, we are not only looking at the shape. What this enables us to do is not only just to see the shape of the structure, it will enable us also to identify the chemistry and the chemical makeup of these very small particles. And that's what I will show next. We can go a little faster here. This is an example of employing this technology to see or to do studies on corrosion prevention of metals. Namely, in this case, we are talking about steel. There are other corrosion protection treatments that are done, and then you need to evaluate the efficiency of these methodologies. One can look at the galvanization, aluminization, conversion layer applications. It's not really that important what process we are looking at. We just want to show or demonstrate the capability of this technique. For example, here we are looking at now, together with the OJ electron spectroscopy that we are doing, this is what's called field emission gun with a super lateral resolution. So these are SEM images. This bar here is 100 nanometers. So we are talking about very, very small structures. The hope is we will be able to identify the chemistry for these nanoparticles. There are simple studies that can be done. For example, we can find the density of particles of various sizes. For example, from the previous SEM image, one could calculate the density of particles that have the diameter of a certain diameter. In this case, for 0.5 micron particles, we see a density of 1 per micrometer squared. Here is a nanoparticle that we want to do the chemical analysis of. So here we are comparing two areas. We have this nanoparticle, and we compare it with the background area. And we can see, just looking at the comparison, this is the energy spectrum. This is the OJ spectrum from this area. This is the OJ spectrum from this area, and we can clearly identify this particle as a copper particle with a background of this is actually an aluminum coupon that has been treated with various treatments to help prevent corrosion on this surface. Often the OJ electron spectrum is shown in a differential mode. So this is the energy spectrum. This is the differentiated energy spectrum, actually, as a function of energy. And clearly, this is copper. There are other, because like I said, because of the advances in information technology, there are lots of things that one can do. For example, you can set what we call a line scan across a certain area to see exactly what the chemical makeup of this particle is. This is, I believe, this scale here. This is a few hundred nanometer particle, and we can see the variation of, say, in this case, we chose to see the variation in the oxygen, the aluminum, and copper. Again, we can see that this is actually copper oxide, because we can see an elevated signal of copper as well as oxygen here. This line here is the aluminum background. So we could do line scans, and in any direction you can choose. The process of arriving at the intensities is pretty complicated, because the signal, remember, this is a very small area, the signal is extremely weak, and you have to be able to look at the signal is basically the area under the curve, but you have to do a proper background subtraction so that you can get the correct answer. There are lots of routines to do background subtraction. I will not go through this at this point. Okay, what else we can do here? So besides line scans, here is line scans in both directions, actually, in the X and the Y direction. This is these are nanoparticles, and here this is an SEM image. On the left-hand side, this is an image of aluminum and the image of copper. The green here is the copper, and the red is the aluminum. This process is extremely complicated, because the way this works is you will have to do OJ electron spectroscopy at every single point, calculate the area, and then convert this. This is not a real image, basically. This is a computed chemical analysis, or chemical image for these two elements. Actually, any number of elements can be done simultaneously. You can do 10, 15 elements at the same time. Here, for example, we've done images for aluminum, zirconium. Now you see here there are two zirconium maps, and what this means is we are looking at two zirconium lines, OJ lines, and they should have a correspondence. This is one way to check. Now even though this may be coming from a different, as you recall, the escape depth is different. 2 minutes? Yes. Okay. Here is one last thing that we can talk about is we can actually also do three-dimensional images, which means you can actually start sputtering the surface. This is what's called a depth profile. So here we are removing the layers from the surface, and as we remove the layers, we are monitoring the OJ signal, and we can see here that these are the different elements. This is the aluminum, this is the copper. We are doing a depth profile on this on this particle. So basically, what we can do is we can do a three-dimensional images using this technology, of course, on a very, very small scale. Thank you.
Thank you, Professor Saleh. Questions?
Yes.
Thank you very much for your presentation. Normally, scanning electron microscope is accompanied by what's called EDX, electron dispersive spectroscopy. How OJER electron spectroscopy information differs from EDX or EDS?
Yeah, that's a very good question. But actually, in one of the slides, I showed you the volume, the analytical volume from EDS is several microns into the sample, while the OJ analysis is constrained to the top few atomic layers. And actually, if you do EDS and AES, they will be totally different images, because in the first, you are looking at the first thousands of angstroms, tens of thousands of angstroms. In the other, you are looking at the top 5 to 30 angstroms only. So this is surface, that's bulk analysis, and that's surface analysis.
Another questions? Okay, thank you, Professor Saleh, again. Next talk by Professor Hikmat Hilal, our colleague from Al-Najah National University, and the title is about charge transfer. You have 20 minutes and 5 minutes for the questions, please. Yes. Dr. Ahid, can you help? Huh. تفضل دكتور. Yes, 20 minutes, 5 minutes. Assalamu alaikum. Assalam. Actually, this work
Assalamu alaikum again. This work is really what we have been doing at Najah University in Nablus, and it's not my own work. I have done little experimental work. Mostly, we train students and then they do the whole job, which is really something from our students and also from our colleagues. Next, please. Next, Ahid. Okay. Many people have participated, many people, but this work is the product of about 15 years or more of research. Actually, I have colleagues. Ahid has been mentioned as co-author because it shows the latest. We focus on our latest. Dr. Samar here, Dr. Iyad, where is Iyad, also has been part of this work. Dr. Najah is away. Many students, I cannot call them. Rola and Rana have been named here because they showed the latest things actually. So it's not my work, really. It's work of so many people, so many colleagues. I'm really proud of their work, and I will show you what we have been doing then. Next, please. Actually, we have collaboration with so many people outside. In France, we have collaboration. In South Korea, we have collaboration. In Saudi Arabia. Okay, we need their help with characterization. Normally, we don't have the characterization. Next slide. This is the global perspective. We are talking about how advanced materials can be used in renewable energy. We are trying to make solar light effectively work. And you can see these pictures are self-telling. This shows how it's too small actually. It shows how the ice extension is going down with time. This is 15 maybe or something, to 2015. Now we are going down as a result of so-called global warming, you know, for fossil fuel. Everybody knows about this. But this is really very bad thing. This is very bad news to neutralities. These here show the again how really the ice extension is going down really seriously in the last 2 years specifically. In the last 2 or 3 years here, we are going beyond the safe average limit for ice melt, our ice extension. This is really very bad news. And this is a real picture from internet, not from mine.
I have never been there, and he is really finding no eyes to stand on. This is bad news. What I want to say is that if we keep doing this, fossil fuel profitability, controlling our life, burning, too much conditioning, too much heating, too much burning, that is bad news for human beings. Maybe in 200 years we all need this, some kind of fresh air on our back. We cannot move in the street. This is if we can follow it. Next slide. That is, and these are consequences, possibly. Okay, it's arguable, but things are really hazardous, and scientists should think about that. Next, please. This is the Palestinian perspective again. In addition to the global perspective, and some colleagues have asked a question, why should we do research, advanced research in Palestine? This is my answer, actually. In Palestine, we have no more economic, we have no more natural resources. We don't have land to build heavy industry on it. We don't have sea. We don't have harbor. We don't have, what do we have, our own infrastructure. We don't have the industry. We don't even have the agriculture. And we just need to say to people, please help us, give us gains, donations. That is no future for Palestinian society. To me, we have to invest in brain and education. We should avoid brain drain, and we should enhance our education, specifically in research. We should follow, for instance, to me, what I can be effective in, and many colleagues here, is materials, advanced materials. You need too much brain, you need too much expertise, you need high-tech, little space, little resources. That is really why Palestinians have to think of investing heavily in this area. We don't have oil, okay, we don't have steel industry, heavy steel industry, but we can make very small silicon chips. We can enhance it, we get commercialization out of that. Perhaps we can subsidize our future economy. I think this is the only way, maybe. It's not a choice. It's not a matter of choosing things. Next, please. Here we are talking about PEC, actually. Photovoltaics, conventional converters, and this is non-conventional now. And PV refers to photovoltaics. PEC refers to photoelectrochemistry. They are basically referred to physics and chemistry working together. In here, you have p-n junction. In here, again, you have p-n junction, but you have a solid semiconductor in contact with a solution, so with an electrolyte. Think of the semiconductor being P or N, then the electrolyte will be N or P. So that is how things happen in PEC, and why I have chosen PEC, actually. Next, please. This is conventional p-n junction. When N-type is brought in contact with P-type semiconductor, you have got here EF thermal level up here for the P-type N. You have got electrons flowing, and then you reach this equilibrium where band bending occurs. This is the basic principle for modern technology, actually. In any equipment in your pocket, in any equipment we have been talking about since the morning, early in the morning, in any technology you are talking about p-n junction technology. So we have to focus on these things. This is NPV. Next slide. Now, of course, it has so many advantages. High conversion efficiencies have been reached, as we will see in a minute. A dry system, reproducible, robust. We can develop it by using tandem cells, but they have still shortcomings as cost, preparation, advanced equipment, environment. When you talk about p-n junction, you talk about, let's say, a chip of, 0.5 millimeter thick. That is too much. To produce 1 meter square of this chip, it costs you a lot. And it costs the environment a lot. You need to do ultra high vacuum techniques, you know that. That's terrible. Next, please. Now, in PEC, things are a bit more simple. you need one type at least. You need N-type, for instance. And the N-type semiconductor is used here. Then you connect it with back contact. This is easy. This is the electrode light, and this is the counter electrode. If light comes here, you get electric current going through here electronically. Here you have got electrolytic conduction. The circle is complete. Next, please. Next slide. Okay. Here, again, this is the electrolyte. Of course, before equilibrium, these band edges should have been flattened. When the N-type is brought into contact with the electrolytic solution, electrons flow here first, and EF goes down. You know from mathematics, I'm sure many physicists know about this simple equations, where if you fill the band, the EF goes up. If you deplete it, it goes down. So you have this band bending system. If you want to make current, for instance, if you want to use a photon to produce current, then you have, this is a photon, it goes here, you excite an electron, then the electron will go this way, there will be a metal contact here, the electron will go up like that, there is here the other, counter electrode. So it's simple, just like in PVs, very simple. Next, please. And our basic strategy was actually, can we manipulate band edge positions? You see how this band edge, can we control it? That was a question we have started 15 years ago. Another thing is that, can we speed up charge transfer? You remember in last picture, we need, electron transfer at the across the. So, then another question was, can we make attachments of these charge transfer catalysts at the surface? Can we enhance strategy of the semiconductor for production of electricity? Can we enhance this for hydrogen production in the future? All of these questions have been really made. And next, please. So this is the simple model we started with. For instance, if this is the flat band potential, VFB, and this is the bending, and this is VFB, VF at equilibrium, this is the redox V. Normally this is not affected too much, this is affected too much. It goes up and down as you wish. Then, if we attach some charges here, can we shift this value? This is the very basic assumption we have started with. Our assumption was yes, we can. Because simply, if we have chemistry here, if we have chemistry students, they know that. In physics, maybe you know it about more in mathematics. But in chemistry, we know it simply. If you bring a positive charge close to an orbital where electrons live, then you lower the energy of that orbital. Very simple. Whereas, if you bring a negative charge close to an orbital, the energy of the orbital goes up. This is what we teach in simple chemistry. And here, we assume the same thing to work in semiconductor and PEC. So attaching charges here, we assume that they will play with the band, with the flat band. Next, please. Okay, we started with monocrystalline solids. All of these have been examined actually. Next, please. And we have seen this. We have attached this positive charge at gallium arsenide, monocrystalline. These have been published long time ago actually. Where is Muayyad? Maybe somewhere here his name appears. Muayyad Masoud has been working on this work. Where is Muayyad? Yes, he has been a pioneer actually in this area at Najaf. He was a student there. Next, please. And these are different attachments. Yes. Next slide. Okay. This is what has happened. Actually, by attaching positive charge to the semiconductor monocrystalline electrode, we managed to control the band edge positions. We control VOC, open circuit potential, etc., etc. Everything has been really, manipulated. Next slide. Ahmed. We controlled band edge positions. We increased efficiency, but unfortunately, by this technique, stability was not enhanced simply because the attachment, which is very costly at the monocrystal, has peeled out. No good. We couldn't manage to enhance it. So our work was good only at the academic level. Next slide. Why don't we do it otherwise? Instead of chemically anchoring molecular species to the surface, we have used polymer-bound positive charges. And this is how it works. This is the metalloporphyrin inside a polymer. This is the semiconductor. This is the eutectic. And this is the wiring. And here you have got the counter electrode. And see what happened then. This is what has been done by Muayyad, actually. Pioneering work indeed, this man. And where is Attiri? Attiri is somewhere away. They have done excellent job in this regard. Next, please. This is the Motchat key, which tells you easily about the value of VFB. And it has been really shifted. So we have been the first, actually. We have been the first to be able to control the position of the flat band potentials by about 300 millivolts by those guys, by those students, which is really great. We wanted to go up, okay. We wanted to go down, okay, we can. And we stabilized it. That was the first achievement. So we have done three things. All strategies have been met. We have enhanced the efficiency. We have controlled the band edge positions, and we increase stability by this very simple technique for monocrystalline materials. Next, please, Ahmed. And you see, this is how stability has been. You know, all of these are in details. Maybe Rola and Rana will be talking about some details of these things. I'm not gonna take it. Okay, next. This was the model. Again, here we have got this equilibrium. This is the semiconductor. This is the electrolyte. When you have photon coming here, it goes up. The electron will go down in the external circuit. Now the hole will go from here to the redox couple. That is very simple. Our question was that if we can lower this, then for instance the electron, instead of going this way, it can go here. Actually, there is a breakup in the picture. This is the catalyst. The catalyst will convey the positive charge to the V redox. So the positive charges are electroactive. They can take the hole, which is the positive charge, okay, from here to here. By this, we have increased the efficiency. We have increased current. And, you know, holes here, when they accumulate, they just break up the surface of the semiconductor. If you can keep releasing them, keep moving them up, then you stabilize the semiconductor. Next. Okay, but next. We have then followed the same technology for monocrystalline, thin film, nanoparticle, not monocrystalline, polycrystalline thin films. We're talking about nanometer scale. We're talking about 200 nanometers. Instead of using 0.5 millimeter thick, you're talking about a few nanometer thick. Next, please. Actually, we have chosen thin films because here, this is well known from DOA. These are where thin films are functioning, and in this area. Thin films are really a challenge. They are not giving good efficiency of conversion. They are unstable. Everybody has troubles with them. We have seen hundreds of papers talking about preparing, characterizing, modifying, but we have seen very few people talking about using them as photovoltaic devices. This is the challenge to us, and we have used our philosophy, the first one talked about. We want to use it for thin film interaction, etc. No? Yes. Okay. Actually, just one thing. Can you go into Ahid? Go. Go. Then again. Again. Yes. أخرى كمان. كمان. امشي معي. بدي بس I want really to reach something. Again. كمل عاد بسرعة. يلا بسرعة جبناك مشان سرعة. بسرعة. امشي. All of these are detailed results. But next. That's it. خلاص. This is the DOE expectation for future thin films. This is the thin film. You know, which one is that here? That is the blue. We are standing up here, okay? This is 2015. We are 2016. They have it up to about 11% conversion efficiency. In 2020, they expected to see it less than 15, okay? We have, by those people, we have reached efficiency of 18%, about 18% efficiency with stabilizing this film. This shows you the potential of those guys, young people in Palestine, to contribute to this advanced area. Thank you, Ahid. Thank you, Sir.
Okay. Thank you, Professor Hikmat. Thank you. Okay, questions.
Thank you. Shukran, Doctor. I want to ask you the PEC type, the analytic with the semiconductor structure. On large scale, how would you produce that on large scale? You showed a small sample with the cell, but I don't have imagination how it would be on a large scale.
Yeah.
One question. The second question is you talked about thin film disadvantages, which are true, that they're unstable, and but they are produced on large scale. You know, Sanyo Electric is producing them in fields miles in the area. Could you comment on those two, please?
Yeah. Actually, in PEC, there was too little time to give the spirit of this talk, but fortunately, I was focusing on certain highlights. I'm sorry, but my students will talk more about in detail, so I will leave the details to them. But actually, in PEC, it has terrible disadvantage. You are talking about liquid, but don't worry, it can be so. With using polymer conducting materials, solid ionics, you know, that will be great. If you talk about solid ionic materials as conductors, we will eliminate the liquid. No problem. Actually, we are working on this. Our new target is to use solid electrolytic system. So this is very simple. As far as area is concerned, don't worry. Very easy to produce. We have limited resources. We use chemical bad deposition, electrochemical deposition. At other laboratories, they are using sputtering. Of course, you can make it a roll on a plastic. Our in future target is to get plastic, you know, polyethylene. You coat it, and then you make a tent with this solar cell. You can make a ceiling. You can cover your truck, you know, with these solar cells. Perfect. And they are flexible. You can tailor them. You can cut them. You can weld them. Yes, that's
okay,
correct.
Thank you. Okay, thank you again, Professor Hikmat. Is about the title is Energy Band Diagram by Olfat. You have 12 minutes and 3 minutes for the discussion. Totally 15 minutes, please.
Assalamu alaikum. We will talk about the energy band diagram and characterization of the indium selenide gallium sulfide heterojunction. Indium selenide attracts much attention for its potential application, and it's very attractive material in order to fabricate new types of optoelectronic device and solid-state batteries in the form of thin films. Gallium sulfide is a wide bandgap semiconductor, about 3.4 electron volt, and it's attractive as photoelectric device and electrical sensor. Also, gallium sulfide is a defect semiconductor. It has a monoclinic hexagonal and cubic crystal structure. Among these, the monoclinic phase is the most stable crystal structure of gallium sulfide. Experimental details. In our lab, we prepared indium selenide and gallium sulfide thin films using the physical vapor deposition under the vacuum pressure of 10 to the minus 5 torr on ultrasonically cleaned glass substrates, and the indium selenide and gallium sulfide film thickness was 1 micrometer, which attached by thickness monitor attached to the system, and the both indium selenide layer and gallium sulfide exhibits n-type conduction. After that, the optical properties of indium selenide, gallium sulfide, and indium selenide gallium sulfide double layer were measured and analyzed in the range of wavelength from 200 to 1100 nanometer, and the data collected using the thermoscientific ultraviolet visible spectrometer evolution. Also, the device was characterized by means of impedance spectroscopy in the range of 1 megahertz to 1.8 gigahertz. Next. Let us start with the optical results. This figure shows the reflectance and the transmittance of indium selenide, gallium sulfide, and double layered in the range of wavelength from 200 to 1100 nanometer. And the data displayed in this figure shows that the reflectivity increased as and transmittance increased with increasing the incident wavelength. And we can see that the reflectivity of indium selenide pink colored and gallium sulfide green colored in the shape does not differ from the shape of reflectivity of the double layered red colored, but the only change appeared in the total magnitude of reflectivity. Next. And the increase in reflectivity above the 200 nanometer is ascribed to the electronic oscillation with the plasma frequency in indium selenide is larger than that with light frequency, and it's readable from this figure that all these layer exhibit different position of patterns, and for the double layer it exhibits some interference patterns with minimum R values at about 590 nanometer, and we can see that the reflectivity or R values collected from the indium selenide pink color is lower than that collected from the interface. Next. For the transmittance, it's worth mentioning that the transmittance behavior of indium selenide is caused by the fact that the photon is highly absorbed by the indium selenide film, and when the energy of photon is equal or greater than the energy band gap of indium selenide, and when the deposition of gallium sulfide on the top layer on the top of the indium selenide change the transmittance properties of indium selenide, and the transmittance of double layer next to that of the indium selenide until it reached about 600 nanometer, then it closed it at about 900 nanometer. Next. All layers showed a good transmittance about 90%, and the double layer is transparent and has maximum T about 90% at about 1000 nanometer. The integrated values for reflectance as well as for transmittance suggest that indium selenide is a potential candidate for the application in selective surface device. The absorbance A was found by from the measured R and T from this relation, and to reveal more details about the optical properties of the double layer, we found the absorption coefficient alpha, which is the K parameter to design optoelectronic device, and use this equation alpha equal A over D, where D is the thickness. In the case of solar cell, by decreasing the reflection of incident light in increasing the optical intensity and optical path of material, and the effective absorption can be increased. Next. This figure shows the relation between the absorption coefficient and the photon energy, and we can see that the absorption coefficient increases with increasing the energy of photon until it reaches about 2.4 electron volt, and this increasing is due to the transition of electron from valence band to conduction band. That means we have two gaps for each sample. Then the absorption coefficient is tend to be invariant or slowly varying with the energy of photon, and both the absorption coefficient of indium selenide pink colored and gallium sulfide green colored are the same and higher than that of the double layer at about 4.14 electron volt. To calculate the direct allowed transition energy band gap, assuming the famous Tau relation, alpha E square E dependence was plotted in this in the figure, and we found the energy band gap by fitting line across the E axis. And as I said, each sample has two gaps. So with the first gaps illustrated in this figure, found the energy band gap for the indium selenide and the gallium sulfide, which were 1.8 3.12 electron volt. With this energy values, the gallium may be a potential material available for fabrication of white lightning device and ultraviolet photoelectric conversion cell. This is the second gaps for each layer, which were 1.6 and 2.46 with indium selenide and gallium sulfide respectively, and 1.38 electron volts with for the double layer. Next. Depending on this optical properties and on the work function of each layer we designed the energy band diagram. Next. We have three material in Ag, indium selenide and gallium sulfide. Because the work function of indium selenide is larger than that of the Ag, so the Ag indium selenide contact can be a Schottky diode, and indium selenide is n-type, gallium sulfide is n-type, so we have n-n junction. Next. To check the applicability of the Ag indium selenide gallium sulfide AU device, the device was excited with an AC signal of a frequency of 1 MHz to 1.8 GHz. The impulse signal was supplied when the device was unbiased. The capacitance spectra of Ag indium selenide gallium sulfide AU interface displayed in this next figure, please. This figure shows the capacitance versus the frequency. As we can see, the capacitance except resonance at 172 megahertz. The resonance was 83, and anti-resonance negative capacitance at 182 megahertz. The capacitance was negative, or 8.03 nanofarad. That means the device, when put the device in the circuit, it converts it from charging to discharging. Next. These properties that are associated with negative capacitance effects nominate the Ag indium selenide gallium sulfide AU device for use as high-speed CMOS amplifiers. In addition, the results of tests revealed the applicability of the device as a switch clock for memory cells and for central processing units owing to its resonance-anti-resonance characteristic. The negative capacitance of the device indicates its applicability for voltage-controlled oscillators. Next. This figure shows the resistance in pink colored and reactance in green colored and impedance in blue current in the range versus the frequency in the range of 1 megahertz to 1.8 gigahertz. And as we can see, the resistance decreasing until it reaches the occurrence, resonance, and anti-resonance. Next. The total reactance and impedance decreases with increasing signal frequency until the resonance-anti-resonance phenomena are observed at 207 megahertz. The reactance and impedance are least at 175 megahertz. Beyond this critical frequency, reactance and impedance decrease slightly. Here, as shown, total reactance is positive, indicating the inductive behavior of the device. It's possible to explain the observed resonance-anti-resonance phenomena by considering that the device's structure behaves as a parallel circuit connecting a resistance, an inductance, and a capacitance, which produces parallel resonance-anti-resonance circuit when the result current of the parallel combination is in phase with supplied AC signal voltage. The narrow bandwidth of resonance-anti-resonance peaks reveals the ability of this device as ultra-fast switch between two states very quickly as the applied voltage changes. Thank you. This is the sub-part of my thesis, and we will do more investigation to get more application for this device, inshallah.
Questions? Yes, Dr. Ria.
Can you show me how you calculate the two energy gap you mentioned before?
First, we plot the absorption coefficient with the photon of energy of photon, and then we plot the alpha E square versus E, and we can see when we can make a slope and intercept with the E axis. That intercept is the energy band gap by tau correlation. Because when found I didn't get here the figure of the alpha E square with E about we. Yes, but I got it.
Okay, thank you very much again. Okay, our next talk is about optical properties of the gallium arsenide by Eman.
Hello, we will talk about the optical properties of the gallium sulfide deposited onto ytterbium substrate. The outline of this talk is introduction, experimental details, structural, optical, and dielectric properties, and finally conclusion. Introduction. Terahertz sensors are important because they are used in many sectors such as telecommunications and biomedicine. In the design of these sensors, one of the most important challenges is the selectivity of the absorber, which can be enhanced through the superposition of the transmission and the reflection. Next. In the lab, we have prepared the ytterbium substrate with a thickness of 1 micrometer and a 1 micrometer gallium sulfide thin films. In another evaporation cycle, gallium sulfide thin films were deposited onto ytterbium substrate, forming ytterbium-gallium sulfide interface with a thickness of 2 micrometer. Some of the obtained gallium sulfide samples were studied by means of X-ray diffraction, scanning electron microscopy, and energy dispersion X-ray analyzer. The optical transmittance and reflectance for gallium sulfide thin films and ytterbium-gallium sulfide interface were measured at room temperature in the wavelength range of 300 and 1100 nanometer. Let us start with the structural and compositional properties of the gallium sulfide thin films. The X-ray diffraction result, which displayed in figure 1A, revealed that the as-grown films is of amorphous nature. For more deep structural analysis, the as-grown films were subjected to the scanning electron microscopic imaging with a magnification of 60,000 and 120,000 of a 7 millimeter scanned area of the gallium sulfide. As you can see from the same images, the same image display intensive distribution of the grains that randomly distributed with an average grain size of 50 nanometer. The random distribution of the gallium sulfide thin films appears in the same images, confirms that the as-grown films is of amorphous nature. On the other hand, the energy dispersion X-ray spectroscopy analysis on different regions of the films revealed homogeneous distribution of elements through the film with the correct stoichiometry of the gallium-2 sulfur-3 compound for most of the as-grown thin films, which were tested over different preparation cycles. However, some samples which are located 5 to 6 centimeters from the substrate center, in addition to the gallium-2 sulfur-3 phase, they displayed the gallium sulfide phase through the films. Next. Testing the films by the hot probe technique revealed that the films exhibit N-type conduction. It is known that the gallium-2 sulfur-3 compound exists in 3 main polytype phases, alpha, beta, and gamma. So the existence of these polytypes in the same field could be now let's move on to the optical properties, starting with the transmittance analysis. The transmission spectra for gallium-2 sulfur-3, which displayed in the black one, revealed that the films are highly transparent, while the decrease in the transmittance of the ytterbium gallium-2 sulfur-3 film, which displayed in the blue-colored curve, could be attributed to the increase in free carriers. Next. For reflectance analysis, as you can see, the whole shape of the reflectance spectrum of gallium-2 sulfur-3 isn't changed when it is deposited onto ytterbium substrate. It is also apparent that the reflectance spectra of gallium-2 sulfur-3 and ytterbium gallium-2 sulfur-3 didn't have the same positions of maximum and minimum reflection patterns. Also, the collected values from the ytterbium gallium-2 sulfur-3 surface are higher than those collected from the gallium-2 sulfur-3 surface, indicating a good polarizability of the interface formed. Next. To better understand the behavior of ytterbium gallium-2 sulfur-3, the absorption coefficient spectra is explored. As you can see, the ytterbium gallium-2 sulfur-3 films has relatively high absorption coefficients comparing with gallium-2 sulfur-3, which means that depositing gallium-2 sulfur-3 onto ytterbium substrate, improving and increase the absorbability of the interface. Also, for ytterbium gallium-2 sulfur-3, additional 2 peaks appeared at approximately 3 electron volt and 3.8 electron volt. To get information about the energy band gap, the famous tau correlation was investigated, and the best fitting of the data was obtained for alpha E square versus the photon energy, indicating the direct allowed transitions band gap. Next. For gallium-2 sulfur-3, for the gallium-2 sulfur-3, the allowed transition energy band gap is 2.98 electron volt, which is in agreement with that reported for gamma phase of gallium-2 sulfur-3. For ytterbium gallium-2 sulfur-3, the obtained direct allowed transitions energy band gap were 1.3, 2.6, and 2.95 electron volt. It is clear that the last two band gaps related to the beta and gamma phases of gallium-2 sulfur-3, while the first value of 1.3 electron volt may be ascribed to the interband transitions through the energy bands of the gallium-2 sulfur-3 films. Next. To give significance for the interference patterns and the resonance peaks which appeared in the reflectance spectra and transmittance spectra, the real and imaginary parts of dielectric constant were calculated from the reflectance data. As you can see, depositing gallium-2 sulfur 3 onto ytterbium substrate raises the net values of the real part of dielectric constant and slightly shift the resonance peak toward higher frequency. Next. Zoom in the gallium-2 sulfur 3 curve indicates that the gallium-2 sulfur 3 exhibit 3 strong resonance peak at 1.32, 2.30, and 2.96 electron volt, and a weak one at 3.47 electron volt. Again, the last three resonance peaks assigned to the direct allowed transitions from the valence to the conduction band of the gallium-2 sulfur 3, and the 1.32 electron volt is mostly assigned to the interband transitions through the energy bands of the gallium-2 sulfur 3 films. To understand the reason for the existing of these resonance peaks, the imaginary part of the dielectric constant were investigated through the programming of the Lorentz-Drude model, starting with the modified relations in front of you, where tau is the electron scattering time, WBE is the electron bounded plasma frequency, WE is the reduced resonant frequency, N is the free electron density, M star is the effective mass of free electrons, and K is the number of observed peaks. Next. As you can see, the experimental spectra was reproduced by substituting the effective mass of electrons equal 0.4 for gallium-2 sulfur 3 and 0.3 for ytterbium gallium-2 sulfur 3, and the tabulated data, please offer. And this tabulated data, as you can see from this computed data, the scattering time of the first three peaks is same, leading to the same mobility of 7.91 centimeter square volt per volt second for gallium-2 sulfur 3 and 9.30 centimeter square per volt second for ytterbium gallium-2 sulfur 3. The resulting reduced resonant frequency, which takes into account the effects of the local fields, such as interband transitions on the dielectric function, continuously increase with increasing incident light frequency. On the other hand, the electron-bounded plasma frequency, which depends on the number of free electron, exhibit a value of 0.76 gigahertz for gallium-2 sulfur 3 and 4.28 gigahertz for ytterbium gallium-2 sulfur 3. Once more, the resonance peaks are attributed to the plasmon interactions. It also means that all electromagnetic signals of frequencies higher or less than these frequencies are rejected. It is a property of a band stop filter. It indicates that both of the gallium-2 sulfur 3 and ytterbium gallium-2 sulfur 3 interfaces are promising devices for use as a band stop filter that operate at terahertz frequency. To conclude, the resonance frequencies are in the infrared, where in the infrared and visible regions, so such devices can be used as infrared laser and for optical telecommunications. Thus, this design seemed attractive for use as resonator in optical receivers. The tabulated optical parameters that are obtained from the dielectric spectra nominate that the gallium-2 sulfur 3 films and ytterbium gallium-2 sulfur 3 as a promising device for gas sensing. And finally, the values of free carrier density and the drift mobility is of acceptable range of thin film transistor technology. Thank you.
Thank you, Iman. Any questions for Iman?
It's not a question just for you, but for several speakers before. I mean, what is the level of confidence that you have when you are determining the band gap? Because from the slides which I saw, I mean, it's not obvious to have the straight lines.
Did you mean this? what here yes First, we investigate tau relation in which we draw alpha E to the power 1 over B versus the electron energy, the photon energy, sorry. The most linear curves means that this is the transitions. Here, the best fitting was the alpha E squared. This meaning a direct allowed transitions. We take the most linear and take the intercept with the x-axis, depending on the tau relation, which is alpha E proportional with E minus EG to the power M, where M may be 2, half, 1/3, and 2/3.
I am sorry if yeah. If you, shall you give me the chance to explain? We usually handle statistical analysis on this. I'm sorry. We usually handle statistical analysis on this data, in which we use the method of residual square sums. Depending on the residual square sums, the lines must cover the most widened region of the data. For example, by tau calculation, which have 4 possibilities of solutions depending on the quantum mechanics, okay? You use the first, for example, direct allowed transition means alpha E square, as the student display now. If you find, for example, 200 data are fitting, and in another curve, not square, but half, for example, 300 data are fitting, so the 300 data is the most suitable solution which cover the data. Thank you.
Okay, thank you, Professor Atif. Thank you, Iman. Our talk now is about the quantum computation and its application to artificial atoms or quantum dots by Anna.
It was the lectures which was supposed. It is cancelled. Okay. I haven't. I didn't know. Okay. So.
Okay, please.
والله ما تجامل
ما شاء الله ونحكي بعدين.
Hello. Good morning. So my lecture will be different from the previous one because I will be dealing with some fundamental problems, not application. I came from Poland. My university, it is University in Kielce. This is the youngest Polish university. And I will be talking about problems which we discussed with my PhD students and also with a group of Professor Pablo Serra from Cordoba University in Argentina. So, okay. This is the outline. After the introduction, I would like to discuss some correlation measure in quantum mechanics of n-body systems. And I will try to calculate this measure for some models which are different kind of models. Some of them are solvable. Some of them are treated numerically. I would like, apart from artificial system, I will discuss some natural atoms. I mean the helium atom and isoelectronic helium series. So the quantum many-body problem, as you all know, because we all are dealing with this kind of matter, is described by the Hamiltonian of this shape, where we have external potential and the interaction between the the bodies which are kept by some external potential. So if there would be no interaction between the bodies, the problem would be separable and solvable. So,
hello everyone. Can you hear me nicely? How was lunch? Good? Okay. Alright. For those of you who don't know me, I'm Safa Hamid. I'm a math professor at Oakland Community College in Des Plaines. It's in the suburbs of Chicago. I'm also a mother of 3 daughters, Dahlia 24, Lena 22, and Dina 16. This disproves the theory of Mr. Al-Hakawati. Where is he? I don't see him. Where is Abdullah Hakawati? He was saying this morning I was too young, so I wanted to share that. To tell him I'm not as young as he thinks. Alright, we have thank you. I like that. Okay, we have 5 speakers for this afternoon session. We're going to start with Dr. Mahmoud Al-Manasra from the Arab American University, Palestine. And his topic is estimation of survival and hazard functions of restricted quality adjusted lifetime. Please help me welcome Dr. Manasra to the stage.
Thank you very much. I'm waiting for the pointer. As she mentioned, I will be talking about estimation of survival and the cumulative hazard function for the restricted quality adjusted lifetime. And so the survival function for the overall lifetime has been studied by many statisticians until recent days, like in the last 2 decades. They start measuring the quality, what's so-called the quality adjusted lifetime, which is like they take into consideration. As I mentioned, we start taking into consideration the quality of life of the patient, not only the quantity of life. And also in the clinical studies, we'll have what's so-called censored data, because the studies usually they are a little bit long, so the data sometimes we miss some data at some points, and we'll have no information about this person or that person for some time during the study or to the end of the study. So we want to talk about estimation of the survival function in the business of censored data when we take into consideration the quality adjusted lifetime for the patients. The first thing I will introduce the old estimator, which is the simple method estimator, Zhao estimator, Wang estimator, and because the last 2 estimators, Zhao and Wang estimators, they are not proper functions. What it means, they are not proper survival functions, which means the survival function is not like it's not going down here. It doesn't keep going down. Sometimes it seems to us like when you calculate it at some points, the survival is 50%, then it jumps to 51 or 52%. So that means the survival estimator here is not survival function. So I will try then after that to find the jump points for this estimator. Then based on this, I will introduce a new class of estimators which are consistent. They will be monotonic, which means they are proper, the estimators will be the proper survival functions. And then after that, I will give simulation study to compare these estimators together. Then probably some of you know the relationship between the cumulative hazard function and the survival function. They are related somehow. So I will introduce a new class of estimators for the cumulative hazard function of the restricted quality adjusted lifetime. Then after that, I will give another simulation study. Let us keep going. And after that, at the end, I will give further for future work. I'm sorry, little bit, it's a bit fast. Yes, yes. Okay. So let me give some notations here. The first thing, we let you be a continuous scalar time over all lifetime, which is for the patients. And we usually like to end the studies at some point. So we define the new thing, which is the artificial endpoint, which is the L. So the TI, we define it as the minimizer of UIs and what and L, which is the minimum, whatever appears first, which is the end of the study, or the person dies before the end of the study, so TI will be that. Then define the quality adjusted lifetime to be the integral from 0 to T. U, it's a given function, known function, which is, it gives you the quality of the life of the patient during the period. And this function will be always between 0 and 1. 0 stands for death, 1 stands for what? Perfect life. Okay? Then we move to the sensor random variable, the sensoring, which is because of the study, as I mentioned before, there will be long studies, so we'll consider the variable C equal to C1 to Cn, be a continuous random variable representing the sensoring time for observation. The observed data, therefore, what's going on here? Okay. The observed data will be whatever appears first, Ti, which is, I define it as Xi, which is the minimizer of Ti and Ci. Whatever appears first, Ci, the sensor time, or what? The death time. Okay? That is strange. I don't know why in this computer. Then the possible, as I mentioned at the last step there, the last step here, I define the based on the quality I calculate of so-called NXI, which is what calculating XI here could be for sensor, then it could be death time, that will be the integral from 0 to XI for the quality of life function. Then our main goal here is to make the survival function at certain points, which is it will be equivalent to say the probability of NTI greater than the point A. Remember here NTI, why this is hidden, I don't know. Chinese. We have the simple rate of estimator will be given by 1 over n, the sum of delta I, which is, I don't know how to get rid of that, but anyway, we have to deal with it. Delta I over the survival function for the sensor data times I in Xi greater than A, which is the like equivalent to the empirical distribution. If you know the empirical distribution, yeah. Now, this is the formula for the simple rate estimator. The problem with this estimator, as I mentioned, it's consistent. It's consistent when you finish, but it's not that much efficient as the other two estimators, which is the Z estimator and the WAN estimator. Okay? So that he came with an idea to reduce the number of sensor data. He said, okay, at certain point we need to consider any observation. If it's considered as sensor at certain point, if it does A, like IXI does A, and it's according to sensor data, like XI stands for sensor data. So in this case, he said why to consider it as sensor. So I can deal with it as depth here. Okay? So he tried to reduce the number of sensor data by introducing new idea. So here he defined xi in another way, which is that if xi dash a, even if it stands for sensor data, he will not consider it as sensor data. And line estimator also he did the same. He tried another way to reduce the number of sensor data. Somehow he came up with an idea, brainstorm idea to reduce the number of sensor data. So as I mentioned, the problem with the last two estimators, they are consistent, they are not monotonic, and they are more efficient than the single weighted estimator. The single weighted estimator is the only estimator who is what monotonic estimator. Okay? Probably when I copy some of them just I copy them and paste them here, so probably we will get. Now the survival function, what I mean here, if you remember, I said it's not a proper survival function, so at certain point when you have A, well, before the survival function, before the point, it will be bigger than bigger than the survival function after the point. So it means if A before A minus S after A, it will be less than 0. That's what means A has negative mass. Okay? So we will try here to find the jump points for every estimator. I am glad here to introduce a new class of estimator. The new class of estimators will be based on the single weighted estimator, which is less efficient than the other. But the nice thing here is what it's monotonic estimator. Okay? And based on the jump points for the single weighted estimator and the Zahu estimator and the round estimator, I will introduce a new class of estimator which depends on them. So I found the jump points for the single weighted estimator here. It jumps up at these points of depth. Okay? Like when A equals xi and delta I equals 1, delta I equals 1, which means what? Which means it stands for what? Did I mention before? It stands for non-sensor depth. Okay, that's what delta I equals 1. When delta I equals 0, which means the xi stands for what? For the sensor depth. As I mentioned, the undergrad image is just efficient than the other estimator. Now, in the next slide, I will introduce the jump point for the Zao estimator. As I mentioned before, Zao we said, okay, if we have an observation which is sensor observation, and if I calculate the NXI with that thing, what to deal with it? It's the best thing. So up to that point, it's passing through. Even though I don't have any information after that point about that subject. So in this case, I don't deal with it as a sensor data. I deal with it as the previous estimator as non-sensor. And at certain point, it will come back. But as A grows, the XI will come back to what? To be sensor. I have to deal with the sensor. And that's why we have what? Negative mass at certain points. The survival function, it will have negative value. And I found all the points that they are three types here. I will be to look at them. Now, after that, I found the jump points for the round estimator. Round, he said, he came with the idea, if we have an observation which is sensor, like if you look at the point here, when we have censored observation, okay, and A equal to NXI, and the sum here, A equal NXI plus L minus XI, like let me graph here something so you can see it, like assume this is the end point, this is L, and this is the vertical, which is 1. Assume we have a sensor at certain point here, the data CI, yeah, which is equal to xi here, and this area I'm talking about nxi, which is the integral here, okay, and this is L minus xi. If I add this to this, and it doesn't pass in, the A is some point here, okay, and if it doesn't pass in, so what considered as sensor? So it will, all in xi, it will be equal to what? 0, yes? And I deal with it as non-sensor the artificial endpoint. Endpoint. Yeah. And those are the rest of the jump points. And I found them, and they are already published. I already published them in one of the journals in the United States. Now, jump points, now I'm going back. Now, I will introduce new class of estimators for the survival function based on these three estimators. But before that, I want to give some general results on consistency of some of that estimator, which is, it will depend on convex linear combinations of these estimators, which is the single weighted estimator and the Wang and Zhao estimators. If we have a sequence of estimators, theta 1 to theta n, for the real valued parameter theta, if we have limit as n goes to infinity of the probability of theta hat n minus theta hat less than some positive number epsilon, which is denoted by epsilon, which is equal to 1, then theta hat n, the sequence, will call it what? Weakly consistent estimator for theta. And the definition of convergence in probability, probably most of you know this. If we have a sequence of random variables x1 to xn converges in probability to a random variable x, then the limit it will be as n goes to infinity of the probability of xn minus x less than epsilon will be equal to 1. My main purpose here to, as I mentioned, to just give the consistency and the mean square error consistency of the new class of estimators, which I am going to introduce in this paper. Okay, I give the definition for convergence in distribution, and I give theorem 1, which is if we have a sequence xn to converge in distribution to x, and yn converges to a number a, which is a constant in probability, then if we multiply yn xn, it will converge to a x in distribution, and if I add them, they will converge into distribution to x plus a. Now, in the lemma here, if we have a sequence, xn converges in a probability to 0, and I define a new random variable, which is of constant. Anyways, which laptop this, huh? Is it done? Yeah. Okay. Let us go back. That's what we introduced the last lemma here. If we have a random variable of numbers alpha n, and it's bounded, and we have xn converges in a probability to alpha n, then we have alpha n xn converges in a probability to 0. Then, if we have 2 here, estimators, theta hat 1 and theta hat 2, be two sequences of weakly consistent estimators of a parameter theta. Consider the sequence. Now I have to give you this sequence. If we have alpha n, theta 1 n plus 1 minus alpha n, theta 2 n, this is the sequence given here. Here. Then theta hat n, which is this, theta hat n, it will be what we can prove based on the results I showed before. We can prove that it's consistent, weakly consistent. So let us move. I have 2 minutes. Now I proved here. I will prove here the weakly consistent for the mean square error for theorem 3. Okay, and I will give a procedure here how to monetize them, and it will depend. I define it as step functions, like I consider alpha n and 1 minus theta alpha n. This is, I will consider it like zal estimator, and this is the single weighted estimator. The single weighted estimator. The single weighted estimator is monotonic estimator. The zal estimator is not monotonic, so I define the theta hat. I'm sorry, theta hat, I will define it this way. Theta hat, it will be 1 greater than or equal. I define alpha 1 here. It will be greater when it's using than 1. Then this, the first step, it's a step function between the jump points, B1 and B2, as long as the variable is between B1 and B2. Okay, we define it as a step function. The first one, it will be, as you know, at 0. At a certain point, it will be the survival function equal to 1. Then at step 1, it will go down and keep going down. So I define the series, which is alpha 1 and 1 minus alpha 1, and I keep going down. I put some constraints here, and I like this estimator to be as close as possible to what zal, because it's more efficient than what the single weighted estimator. But the single weighted estimator is what? Is monotonic, and I want the new estimator to be monotonic. So I will choose alpha or ANs, I will call them ANs. I will choose them so that what? So it will be closer to this and farther from that, but to keep it what? Monotonic. So I will be just maximizing the sum of AIs or alpha I's here, because I'm using alpha I's. Because the alpha I's here, what? If I maximize this, it will be closer to this, which is more efficient than that. And I did simulation study here. I'm going to move faster. Those are the estimators. This is the simulation study. If you look at different ends, let us go back to the means. I calculate the mean square errors for the single weighted estimator, zal estimator, Wang estimator, and the monotonized zal estimator, and the monotonized Wang estimator. I came up with those two. If you look at the mean square errors for n equal to 5, if you look at the first line and second line and third line, even though they perform better than what the mean square errors for zal and Wang here itself. And the advantage we have here, the monotonized zal and the monotonized Wang, what they are monotonic estimators, so they are much better than the older estimators.
So Dr. Manasa, can you add?
Just a minute. For n equal to 50, if you look here, even like I keep increasing n, the sample size, and if you look at them, probably you can see what they are either very close, the efficiency of these estimators very close to each other, or what sometimes even the monotonized value and the monotonized value they are much better than the single weighted and the Z. And unfortunately, I have these results with me. The comments, it's like, as I mentioned, they give you some information about these results, how we can get to the idea that the monotonized Wang estimator and the monotonized Zhao estimator will be much better than the other two estimators. Thank you.
Thank you. We have 2 minutes for Q&A, so if you have any questions.
Actually, I have two questions since I have the same idea about this survival function. Biologically, you describe that the survival function sometimes become negative.
Yes.
How you can explain
Not
it?
negative, not negative. At certain point, it used to be like 50% the survival function when you calculate it at certain point. Then right after that the point, it will be 51. And that's why we don't call it survival function. We call it survival. It's a point estimator in this case. I believe it as point estimator.
This is not
And it's not bad.
This is not my question. My question, biologically, how we can describe it? Biologically, how we can describe it? You take the limit from the left and the limit from the right, the limit of the survival function, and then you take the difference between the two limits. The limits become a very, very small negative number. So you describe the survival, the point estimator of the survival function is negative.
Not exactly. We are saying the point itself, it assigns negative mass, but the survival function itself is the
This point, the point negative mass, what that mean?
Which means the value of the survival function right after the point is bigger than the value of the survival function just before the point.
The individual become
Individual.
high risk.
Yeah, like I calculated as I mentioned.
Another question.
If you look, like assume we have negative mass at the point 9. So just before 9, if I calculate the survival function for that, minus the survival function for 9, right after 9, it will have what? It will have negative, which means this is bigger than that. This is logic like, as I mentioned, the survival function, I calculated a certain point, 50%, then right after the point become 51%.
To deserve the time, sorry, Doctor, to deserve that time, I have another question. Is that your estimator can be generalized to any type of sensory data?
Not,
We
we are working with that with some of my students right now, like when you have interval estimator, when you have left sensoring, we are working on this. But I'm sure it will work for hopefully. That's our hope.
Thank you. This was an awesome talk and very, very good questions. I'm sorry we cannot put any more questions. If you still have one, please sit next to Dr. Manasra at dinner time and bombard him with your questions. Thank you. I believe our next speaker is from Gaza, isn't it? Is he connected with us via Skype? Alright, the next topic is existence theory for fractional differential equations by Dr. Muhammad Matar from Al-Azhar University, Palestine. That's fine. That's fine. You can start, yeah.
Thank you. We wish the same. We wish the same. Hopefully in future conferences you'll be with us in person. Thank you. Bye-bye. Alright, I think this takes us to our first talk for the day. It seems to me it's a lighter topic than the ones we have been handling. The topic is a comparison study between students at three Palestinian universities using the multivariate regression model. Our speaker is Tiran from Al-Azhar University, National University, Palestine. Please help me welcome Tiran to the stage. You have 15 minutes. I'll learn you in 2 minutes. Good afternoon, everybody. First of all, let me thank the Arab American University for this wonderful conference and the conference committee and for invitation. Also, I would like to express my sincere gratitude and appreciation to my supervisor, Dr. Mohammed Asad from Al-Azhar National University. Unfortunately, he is not with us today. My article title, as you see, a comparison between students at three
Palestinian universities using the multivariate multiple linear regression model. First of all, what do you mean by regression analysis or regression model? Regression analysis is a statistical methodology which is widely used in various fields of science for estimating or studying the relationship between variables. These variables are divided into independent variables or what I will call explanatory or predictive variables and dependent variables what I will call the reference variables. So when we want to study or describe the relationship between the explanatory and the reference variables, the methods used to study the relationship between these variables are called regression methods. We have four types of regression methods. The first one in the simplest form is a single linear regression method. The second one is multiple linear regression method. Third one is the multivariate linear regression method.
First presentation is remote simulation of the time-dependent network equation by my missionaries from Al-Quds Open University, Palestine. Please welcome Mary to the stage. Thank you.
the Maxwell's equation. The Maxwell's equation, electromagnetic phenomena is spread everywhere here in our devices. When we use electromagnetic devices, mobile phones, etc., internet, and any other devices here based on electromagnetic phenomena. The Maxwell's equation then tells the basis of the classical electrodynamics, which describes an extremely wide range of physical phenomena observed in nature and used in various engineering devices. Computer modeling of propagation of electromagnetic waves and their interaction with matter, based on the numerical solution of Maxwell's equation. Now I will go to the definition of Maxwell's equation. Nearly all of us heard about Faraday's law, Ampere's law, and Gauss's law for electric field and magnetic field. Faraday's law is, as you see, the curve of the electric field. Here are some you don't know. A is the electric field intensity, and B is the magnetic field density. So the curve of the electric field is equal to the partial derivative of the magnetic field B with respect to time. It means that the rotation of the electric field gives a magnetic field that's in opposite direction. Ampere's law, which is the curve of X, which is the magnetic field intensity, equal to the current density plus the partial derivative of D with respect to time. D is the magnetic field density. This term is produced by Maxwell, James Clement Maxwell. It is called ZD, which is the displacement current. Gauss's law for the electric field, the divergence of the give us the rho is the charge density. Gauss's law for the magnetic field, which is the divergence of the magnetic field, gives zero because we have no magnetic charge. Now applying the divergence theorem and Stokes theorem for Maxwell's equations give us Maxwell's equation in integral form. Faraday's law, if we take the first equation in the differential term and integrate it, we have the integration as replaced by E that dl equal to the minus the derivative of the double integration, which is the surface integration over B. And Ampere's law is the same. It's seen to be version of the PowerPoint, not as I use, so something is missing. Ampere's law and Gauss's law for the electric field and Gauss's law for the magnetic field. Gauss's law for the electric field, if we integrate over a closed surface, we have the integration over the volume of the rho V, which is the volume density, charge density. Gauss's law, if we integrate, we have for the magnetic field zero. Now there is a great relationship between Maxwell's equation and potential. If we use this transformation, electric and magnetic field can be written in terms of a scalar, its mean scalar electric field, and vector magnetic field to transfer it to potential as follows. If we take the first equation, E is equal to minus the gradient of Z, where V is the scalar electric potential, minus the partial derivative with respect to time of A, where A is the vector magnetic potential. Then and B is equal to the curve of gradient relation sub E is equal minus the gradient of V, the scalar potential. Now applying these two equations as before, we reduces to Laplace equation if rho equals 0. Since the potential is a scalar function, this approach has advantage over trying to calculate the electric field. Once the potential has been calculated, the electric field can be computed by taking the gradient of the potential. Laplace and the Zane equation in two dimensions, and we know Laplace and the Zane equation in two dimensions, that expressed here by delta square of phi equal to the second partial derivative of phi with respect to x and the second partial derivative of phi with respect to y equals 0. This is Laplace equation, and if it's equal to f of x and y, where f of x and y is a given function, it's a Bayesian equation. Now solving Maxwell's equation using a finite difference time domain method, applying this figure is clarified by star, we can calculate at any point the value of the potential by taking the average of the surrounding curve abundance and it. The finite difference techniques are based on approximates, which permit replacing the function equation by the finite difference equation. These finite difference approximations are algebraic in form. They relate the value of the dependent variable at a point in the solution region to the values at some neighboring points. Constructing finite difference approximation from a given differential equation involves estimating derivatives numerically. The finite difference time domain method employs finite differences and as approximation to both the spatial and temporal derivatives that appear in Maxwell's equations. Then phi, which is the potential at any point in the domain D, is the average of the values of phi at the four surrounding points in the 5-point stencil of this figure, and this corollary is the basis of the iterative method. Now using this notation, the Laplace and the Zane equation respectively gives the Laplace equation, if we use the figure before, and the Bayesian equation. Hence the Bayesian equation delta square of phi equal to f of x and y. This is known as the phi-point equal and difference equation using figure 1 in the and the Zane equation in two dimensions should be expressed as missing. If we take an example of two-dimension finite difference time domain method, now if we have the shape, a rectangular shape or a square shape, if we have a rectangular shape or a square shape, now we have a square shape 4 centimeter by 4 centimeter. It's a result to if we have the voltage equal 0 and the voltage equal 0, here in our example the voltage also equal 0 and the voltage is given by 10. And we want to calculate the potential inside. We can calculate the potential numerically by any numerical methods, but we analytically by any analytical method, but we now want a numerical method which is finite difference time domain method to calculate it. So it's our job to discretize the shape. I discretized it as this. We want delta x to be equal to delta t, which is we use x in the equations. I used x to be 1 centimeter, and here I named the points this as v1, v2, v3,
said, thank you. Thank you, Shukra. You're doing awesome as an audience. You have one presentation to go. Does anybody speak French here? Awesome, because the last speaker is either from France. In first minute, some French guys. You see it? No, the two speakers are from France. Yeah, I totally understand, but because he's speaking from France, and plus we need some French coming back. That is the previous track. It seems to me I'm confused about something. Last speaker is speaking some French, right? Do I start? Okay. And in case we need some French, I need to make sure we have someone who understands French. Thank you. Are we connected to the speaker? Hello, Dr. Tucker. Can you hear me? Good. I'm about to introduce you to our audience. So just give me a minute to introduce you and introduce the topic that we're talking about. Just give me a second, okay? Thank you. Yeah, just give me a minute to introduce you. Well done. Alright, so the last step is parallel comparisons of chi-square, Kaliningrad, Saman, Anderson Darling, and Bitter resin tests by Dr. Yusuf Ataka. Okay. Alright, thanks a lot. We're ready to go. Good luck. You can start. You can start. Thank you so much. We really enjoyed your talk. I believe that your email address is in the schedule for the conference. If anyone has questions, is it okay to send you a question by email? Perfect. Thank you. Merci. Bye-bye. Bye. A very good job as an audience. Thank you. Enjoy the everything guys tonight. Yes. What? I'm not saying that. I'm talking about my own session and then saying. So you have like 15 minutes break. The coffee rest. Then okay, you'll have 1 hour
didn't leave it too.
choose u equal to 1, identical to 1, you get what is known as the two-dimensional Kermack-McKendrick model for the spread of epidemics. So you can think about the Zika virus, for example, now that we hear about. And this is supposed to be a good model for this type of solution of problems. Sorry. Here, X is the number of people who are suspected of being infected, and Y is the number of people who are really, we know that they are infected here, infected carriers, okay? So my colleagues from Romania, what they did with this model, they computed what is known as the feedback linearization of the model. This bit complicated, the calculation. It looks like a simple transformation, but it's more complicated than that. It's not just making a change of variables. Notice here, it's important that the Z2 is negative in this transformation, because it's Y is positive and the parameters are positive, so this becomes negative. And my colleagues computed the feedback linearization of this model, and they obtained this new model in Z1 and Z2. And from this point, my collaboration with them is that I would consider a stochastic version of this model now in 2 dimensions. So I think most people would agree that the spread of like a Zika virus, I mean, it's random. I don't think it's deterministic. It's more realistic to assume that you have some noise. So if you're not familiar again with stochastic processes, so you add some noise here, which is W is a Brownian motion or a Wiener process. And if you like physics, some people call it the Wiener-Einstein process. It depends on the people you talk to. So we have a function V, which is the infinitesimal variance here of the process. And you have the same model as before. So just added some noise. And I will consider a stochastic optimal control problem. So I define what is known as stopping time in probability. So I define T of xy to be the first time that y is the number of infected people. The first time it will go to 0, assuming that we start with x and y at first, which are positive. Okay? And in terms of the new variables, t and tau are the same. Tau is the first time z2 is equal to 0, but it starts from below 0. It's negative first. Okay? So in control, you need a cost function that you want to minimize. I mean, it must be optimal with respect to a certain cost function. So just to go back, this is, if you don't know much about control, this is classical. You have, it's linear in U in this equation in Z2 dot. And the cost function is assumed to be quadratic in U. That's, again, very classical formulation. It's just that I have a minus in front of the U squared because Z2 is negative. So the cost is positive. And I have also gamma here, gamma constant. And we want to find a value of U that will minimize the expected value of the cost. It's random. I mean, you cannot minimize the cost, the expected value of the cost only. And if you look at this parameter gamma, I mean, between 0 and tau, the final time, which is random, you have some cost. So you want to end as soon as possible. So you can say that the aim is to minimize the time it will take to bring y from y of t from y to 0 here, and taking the, but you must of course take the quadratic control cost into account. And I think yesterday with some people talk about the usefulness of mathematics and some models. This one, I mean, that's not my model, it's quite a famous model. And I think the problem is natural. I mean, you want to bring the number of infected people to 0 as soon as possible, but you have to respect some constraints, like you have some quadratic costs that you must take into account. This is what is known as LQG homing. L because it's linear in U, the definition of the model. Q because it's quadratic in U in the cost function. And G is because we have Brownian motion, which is a Gaussian process. And homing because you want to bring the process here to 0. Okay? So this is the type of work I've been doing for many, many years since my PhD. And I know that to find explicit solution to these problems is very difficult in more than one dimension. Even one dimension is not easy, but here is 2 dimensions. So I was not sure at all when I started to work on this problem if I would be able to find an explicit solution. But I've been able to do it for this model in particular using a method which is known, most people must know about it, but method of similarity solutions to solve an ordinary PD partial differential equation. Okay? So what is the optimal solution to our problem? So again, if you're not familiar with control, you define what is known as the value function, which is the best you can do. So the infimum of the expected cost for u between 0 and final time tau. Okay? But it's quite difficult in theory to find the optimal control between 0 and tau, but you use dynamic programming. Okay? Dynamic programming, again, if you don't know about dynamic programming, you use two results. First one is Bellman's principle of optimality, for which I think he had a prize, no, for this idea. And Taylor's formula, that's all. I mean, one is stochastic, it's a bit more difficult, but still it's not very, very hard. So you get dynamic programming equation. You find that the value function satisfies a certain equation here. That's a partial differential equation. And the main point is that in this equation, u is u at time 0. So instead of having to find the control between 0 and tau, you only need to find the control at time 0. And that's the idea of dynamic programming. So if you look at this equation, u appears u square here, and you have u there. So you differentiate this equation with respect to u, and you obtain an expression for the optimal control in terms of f sub z2 here. So you take this expression, you substitute into your dynamic programming equation here, 3, and you obtain a nonlinear PDE second order. So when I have a new graduate student, for example, who doesn't know much about stochastic processes or about dynamic programming, I say, well, you start from here. Now it's a problem on differential equations. You don't have to know about the rest for the moment. Just trying to solve this equation, which is a second order nonlinear PDE. So it's not obvious. You need some boundary conditions. The first one is that if you start at 0, what the time it takes to reach 0 is 0, so the cost is 0. But that's only one condition. Normally you won't be able to get an explicit solution. So I found a second one, at least. If Z2, which is just a constant, negative constant times y, so if the number of infected people tends to infinity, I assume that it will take an infinite time to go to 0, so that f will be equal to infinity, or maybe the optimizer will be able to do it infinite time, but using infinite control. So the end result is the same to me. So you will have this function tends to infinity, so that's two conditions I can use. And now, as I said, these problems are very difficult to solve explicitly. And what I'm doing is trying to find some special cases where it works. I don't like numerical methods. I don't like, I don't know, approximate solution. I like exact optimal solution, but it must be in special cases. So here I assume that the variance, infinitesimal variance, is of the form a constant times z1 times z2, which is negative. So of course the variance must be positive. And you make a transformation. You define phi or phi as the exponential of minus alpha times f, the value function. Alpha is a positive constant. And this transformation is quite useful. You get now a linear PDE, second order linear PDE that you must solve. That's your new boundary conditions in terms of phi. So because it's exponential of minus alpha f, so at 0 it's 1 and the limit is 0 instead of infinity. Still now, okay, it's a differential equation problem. Are we able to solve this PDE explicitly with the conditions that we have? So my favorite method to solve these equations is method of similarity solutions. So you're trying to use some symmetry arguments. So here, if we assume that the solution will in fact depend on the ratio minus z2 over z1, which is non-negative. So you have to be lucky for it to work, but it does here, because you take your PDE and you obtain now an ODE, which is the following equation here that you must solve, and now you must be able to express your condition in terms of what is known as the similarity variable. This is what I get here. So when z is equal to 0, if z2 is 0, z is 0, and we have also this condition here that z tends to sigma as Z2 tends to minus infinity, so I get my new conditions. And now, if you use a software like Maple, which are the one I use, Maple was able to give me an explicit solution to this problem, ODE problem, with two conditions. I mean, I've been working for 30 years on this type of problems, and that's the first time I've seen this function. It's a special function. It's a German, I think, Hoin function, Hoin B function. So it's a special function. Of course, it's defined as the solution of a certain differential equation. And to make it simpler, I chose the simplest case possible. All the constants are equal to 1. Alpha is also equal to 1. And my equation is this one. So again, Maple is able to solve it. It's just a special case. And it gives me an explicit solution with two, of course, constants to determine, C1 and C2. And it was not obvious to me at first what are the values of C1 and C2. So I defined the first term here above. I called it Psi1. And the rest was Psi2. And I won't give all the details, but it's quite straightforward to find that using the boundary conditions, the condition that we had, we can find that the constants are equal to 0 and 1 respectively. So I get my explicit solution. That's what I like to do as a researcher, to get exact solution to this type of problem. So the solution is in fact Psi2 here. And it's not an obvious function. So I use a Maple to see what it looks like. It is exactly what we were looking for. It's very logical the way it behaves, exactly what I wanted. And from this function, if we want to obtain the optimal control, well, from the formula that we had, it's just minus the derivative of f with respect to Z2. So this is the problem that I think I solved exactly. That's what I wanted to present at this conference. Would be me giving more details, but between the time I submitted my abstract and the conference, I try also to work on the three-dimensional model, because Kermack-McKendrick can be in 2 or 3 dimensions. And this is a version in 3 dimensions. So this is my own work, has nothing to do with my colleagues now. So we add a new variable now, which is Z, which is the number of people who are removed from the population, are isolated. And again, we have this noise term, which is added. And we have a linear term in U. If you, again, you're not familiar with stochastic processes, when you model certain phenomenon like this with Brownian motion in a few minutes, I will assume that V is a constant. If V is a constant, it means that this term here is a Brownian motion. Okay? Brownian motion is Gaussian, as I mentioned. So it means that you accept that in theory, x can become negative for any value of t. A negative number of infected people, I'm not sure that's very realistic. So unless it's between 0 and -1, which we say you round to 0, or you can change the application. Maybe for some other application it would be more realistic. But here you have to accept that x could be negative in theory here, and so with a certain positive probability. So it's just a model. And we'll try again to solve an optimal control problem. Here we have, okay, B is not 0, V is strictly positive. Here, that's what I do normally when I try to solve these type of problems. I assume that if U is equal to 0, you reduce your model to a very simple or a known model like here, Kermack-McKendrick model, which is the case. If you take U equal to 0 and B, you remove the noise, you go back to the model which is well known. Okay? So again, I'm looking for a certain problem, which maybe not maybe completely realistic, but that I can solve exactly using mathematics. And here I define this first passage time, the first time that the sum of the 3 variables will be equal to 0. So we could say if we accept the fact that x can become negative, it's when the epidemic will be over, completely over. Okay? We can also change a little and say the first time that the sum will be equal to a positive constant, but small positive constant, which means that it's really under control. Okay? The important thing is that it depends on the sum for my work to be okay, to be able to solve it explicitly. I must assume that this time depends, first passage time depends on the sum of the three variables. Okay, again, we have to define a certain cost criterion. So it's very classical again. You have a positive constant, a positive function, sorry, times u square, plus a lambda, which is what I use normally for my work, lambda for the parameter here. In the previous model, lambda was already used, so I use gamma instead, but I'm used to lambda. And you want to minimize the time it will take to end the epidemic here. You must take the control cost into account, of course. So you define the value function, and when I started to do the calculation, I was not optimistic because already in 2 dimensions I had this point function, but obvious, and now I'm in 3D. Okay? Normally you won't be able to do it. That's all. I mean, you have to use numerical methods. I don't know, but I tried it anyway. So you define the value function, and you use dynamic programming. Again, you have this dynamic programming equation. You have one boundary condition, which is that if you start on the boundary 0, that's here nearly true. And I wanted at least a second condition. So if x, y, or z are increased, f must increase also. If you have more people who are involved in the epidemic at first, it will take longer to bring it back to 0. Okay? So I think it's obvious. From the dynamic programming equation, you find immediately that u star is equal to minus b over q times f sub x. You substitute into the dynamic programming equation, and you obtain again a nonlinear, second-order nonlinear PDE. And I will try to get an explicit solution to this equation. Again, for my students, sometimes they don't understand anything from the beginning until here. But now I tell them, try to solve this equation. You don't need to know anything about stochastic processes. So use the method of similarity solutions. I assume that my solution will depend only on the sum, which is a similarity variable. That's why I said previously that if I change 0, if I replace 0 by a positive constant, I think it will be okay, because the important part is that the function must depend on the sum here. And if you try this similarity variable, you end up with a Riccati equation, and this is my condition. H of 0 is equal to 0, but again, it could be H of 0 equals a constant plus delta, anything. And this is a Riccati equation for the derivative of H, which I call G here. Okay? So this type of equation can be solved by a software like Maple. I have this proposition. I have a colleague in my university who worked for 50 years, I think, teaching differential equations. And he didn't like this method. He knew it, but he didn't seem to like it. And I tried to convince him that it was a good method. And here, if you want it to work, all the terms in the equations must be expressed in terms of W. Of course, if you cannot express everything in terms of W, it fails first. So V must be a function of W, and also the ratio B squared over Q must be a function of W. So the simplest problem I can, that was my proposition, if we can say that B squared over Q and V depend only on W, it means that in theory we're able to solve our problem, in theory. So the simplest case I could think of, suppose that B is a constant, non-zero constant. Q is also a positive constant, which is classical. And V is a constant V0. So that's what I said a few minutes ago. So we assume that you have a Brownian motion so that X could become negative for any value of T. Okay? So that's the weak point if you want, but that's something we have to accept. So to simplify the equation, I assume that I denote, in fact, B squared over Q by gamma. I have this nonlinear with B squared because I didn't use the transformation to linearize it. I didn't have to do it. So that's an equation that Maple was able to solve. I got this explicit expression here. but I still have one constant to determine. And I was not sure how I was able to do it at first. So again, I simplified as most as possible. I chose all the constant equal to 1, and this is the new solution that Maple gave me. And I have to find what is this value of C, because that's where I use my second condition that says that H must be increasing with W. F is increasing with X, Y, Z. So if F is increasing, it means that H must be increasing too. So you just compute the derivative of this function, and you obtain this expression. So it's trivial. And then I said, well, it's supposed to be increasing for all values of W. So what happens if W tends to infinity? And I obtained this solution, this expression, minus square root of 2. So I said, okay, it seems to fail. It doesn't work, because I was at a strictly increasing function. It seems that my solution for any value tends to, the derivative tends to minus square root of 2. So not right, except if you look carefully. Softwares like Maple, I mean, they are not very careful with that, but if you look at this expression, there's a special case. If C is equal to minus 2 square root of 2, you have a problem here. So you have to consider this case in particular. And I was very glad to find out that if you choose this value, exactly minus 2 square root of 2, well, your function becomes square root of 2 times W, it's linear, and the derivative is positive, exactly what you want to obtain. And that's the only case that works, only one. So that's my constant. I have no choice to say that C must be equal to minus 2 square root of 2. And I obtained this proposition that in this case, which I found very surprising at first, in 2 dimensions, I had special function as solution. Here I'm in 3D, and the constant, the control, optimal control is the constant, minus square root of 2. So it seemed to be simpler in 3D and in 2D. That's surprising to me. I found the constant for the simplest case possible, but I was able to generalize. If we have B0 different from 0 and positive constant, this is the only value of C that is possible, and you get your new expression for H, which is the value function. And also, you have the explicit solution for the optimal control. It depends on the sign of B0, but it's a constant times the sign of B0. So that's my second part, my talk, just to conclude with a few remarks. So as I said, I don't like numerical methods, I don't like approximate solution, but when I'm not able to solve exactly using the method of similarity solution like here, we could at least try to find some approximate methods. In 2D, if my choice of V is not realistic at all, people would say, like my Romanian colleagues are better than me with numerical methods. Maybe if we really need to solve a problem more realistic, maybe we could use numerical methods. In 3D, I use a case when we had only constants, but it's not necessary. There was this proposition 3.1 that said you must have certain relationship. Okay, perfect. So in this proposition, it's not compulsory that all the functions are constant. So we could try to find optimal controls in different cases, maybe more realistic. And we can, if we're not able, we can try to find some suboptimal controls. I've never liked to settle with suboptimal control, but I tried it a few years ago. We were very surprised to find out that first it's more difficult to compute sometimes than the optimal control, because you cannot use dynamic programming and so on. And also when you manage to find a suboptimal control, which is like, suppose you assume that you want a linear solution, finding the best linear control, to me, it's more difficult than the best control sometimes. And if you find it, I used some particular example, and I found out that the difference between the optimal solution and suboptimal solution is very, very small, very small. So again, what's surprising to me, that doesn't make much difference sometimes if it's optimal or suboptimal. There's a few references. That's my 2 Romanian colleagues that's working on this problem. I wrote many papers on AQG homing. That's 2 that I wrote with my former PhD student, Zituni. this is my former supervisor who introduced this subject at LQG Homing. I have my last slide.
Thank you.
Okay, so thank you for your talk. Just a small question, please. So when you show your cost criteria, cost function in the beginning, so I saw that the upper limit of the integral is tau of z1 and z2, right?
Yeah.
Okay, so tau is a random variable.
Yes, that's the difficult part. That's the original part. Not many people work with the final time, which is random. And many people don't see the difference because if it's a fixed final time, that's trivial. That's very well known.
Okay.
But if you have a random final time, that's another story.
Okay. Now, so you are using the dynamic programming principle of Bellman, right?
Sorry,
you are using the dynamic programming principle of Bellman. As far as I know, that using the dynamic programming principle, I think we need to transform this cost functional to an equivalent one with deterministic upper limit.
No.
Yeah?
No. Really, no. I'm sure, 100% sure that what is different is that the boundary conditions are different. But you don't have to have it's in the famous book by Fleming and Richaud. This type of problem with the final random time, I'm not the only one. My supervisor was not the first one, but it's not many people find explicit solution. But you can have a finite time which is random. That's not the problem for the dynamic programming equation.
Okay.
Okay. Yes, but you have to be lucky to find explicit solutions. I mean, thank you. I'm glad you say that, but I mean, when I try to a new problem, I'm not optimistic, I would say. I mean.
Okay, thank you, Doctor. Now with Abdurrahim Musa from Birzeit University. This is a presentation titled by Optimal Life Insurance Selection and Purchase within a Market of Several Life Insurance Providers.
Okay, so thank you for the introduction. Good afternoon, everybody. First of all, I would like to thank the organizers of this great event. Well, I'm going to present a work that is related to some work of Mario. We will see some similarities here, and probably we'll see also some similarities for the work of it's good like this? Okay, excellent. So the title of my work is Optimal Life Insurance Selection and Purchase Within a Market of Several Life Insurance Providers. This work is joined together with Professor Alberto Pinto from Porto and Diogo Pinheiro from Brooklyn College of the City University of New York. So the idea here is that we have a problem faced by wage earners. This wage earner has uncertain lifetime, which is going to be assumed a non-negative continuous random variable. We will call it tau. And this guy wants to make decision concerning three strategies. So the first strategy is consumption. So he's consuming from a market. And the other strategy is investment portfolio. And the third one is life insurance purchase. So concerning consumption, we will find the optimal strategy for him. And now, concerning the investment portfolio, we assume that this guy invests his all saving in a financial market, and this financial market consists of free market. So he puts a fraction of his money in the bank, and he gets like some interest in the end of the year. And also he invests other part of his money in the financial market that consists of, let's say, finite number of risky assets. So that's what concerns like the investment. Now, concerning life insurance purchase, we will introduce a insurance life market model. So for this insurance market, we will consider a finite number of life insurance providers, let's say K insurance companies, and the guy wants like to insure making buying life insurance means that he signs a contract with the insurance company that he likes to insure with. Okay, so the idea of this work, so basically this work, the motivation of this work comes from, it's relevant to mathematical finance. So here I'm showing 3 recent research articles in this context. The first one, it's an optimal investment decision when the time horizon is uncertain for a consumer. But here in this paper, no life insurance. Okay, so 1 year later, I think, yeah, that was in 2008. 1 year later, Pliska and his PhD student modified or like make some improvement on this paper, and they include some kind of life insurance, you see here. Yeah, but that paper like was talking about only one prime emotion, I think, and then a few years later, the authors here like make some development on these 2 papers. They include optimal life insurance purchase, consumption, investment in a financial market with multi-dimension diffusion terms. But here, they were considering only one life insurance providers. And in real life, you see sometimes you don't like one, you go to other. So what we are going to do is to generalize all these papers by considering like arbitrary but finite number of life insurance providers. So I'm going to get to so the outline of my talk will be like this. The problem formulation will consist like sorry. So we go back like this, right? Yeah. So the outline of my talk is I will introduce the financial market model, and then life insurance market model, wealth process, and then we will see the stochastic optimal control problem and how we transfer this to an equivalent one with deterministic time horizon, so that we can use dynamic programming techniques to derive a partial differential equation, which is called Hamilton-Jacobian-Perelman equations, that relates to the famous guy Perelman, who initiated this partial differential equation in 1950s. And then we will derive the optimal strategies explicitly. We will see some functions there. And if we consider an example, CRA to the functions, we will see also the optimal strategies in terms of these utility functions. Okay, so let's go ahead now. Okay, so here the setup. We fix a positive time in the future. We call it deterministic time horizon, and we have a complete probability space. And we have m-dimensional prime motion. F is a filtration generated by the increments of the prime motion. And now our financial market model, as I said before, consists of free markets. So that's S0, whose prices evolve with time according to this ordinary differential equation, and the other risky asset prices, whose price is Sn, and these prices evolve with time according to this stochastic differential equation. Okay. Now, so we assume that the wage earner is alive at time t0, and his lifetime is a non-negative continuous random variable that is going to be completely independent of the filtration that's generated by the increments of the prime motion. And the random variable tau has, we assume that has a distribution capital G minus with density small g. So, so that this identity holds. So now the survivor function G plus is going to be the complement of G minus, and it's defined as the probability for this guy to survive past time t. and this is the complement. And the hazard rate function is the conditional instantaneous death rate for the wage earner surviving past time t. Is going to be given by lambda, and lambda is going to be the fraction between g and capital G plus. So like that, we can move on to the life insurance market model. And as I said, we have K insurance companies, and the wage earner buys life insurance company from the KIF insurance company by signing a contract with the KIF insurance company. And if he signs a contract, then he has to pay money for the insurance company. We call this premium. Okay, and at each instance of time, he has to sign only one contract, so he can change all the time. Now, if the wage earners die before capital T, so tau less than capital T, so his family gets this money, and this is going to be a big amount of money. We call it capital Z sub K. And it's going to be the fraction between what he pays to that insurance company over a function that determined by the KF insurance company itself. So etas are going to be different among the insurance companies. And this eta function is a function determined not by the wage earner. It's going to be determined only by that insurance company. So each insurance company has its own self policy. Now, okay, so what the total amount of we call it total legacy of the wage earner at time tau less than or equal capital T is going to be Z, initial wealth, plus what he gets out from signing contracts with the insurance companies. Now, concerning the wealth process, so the wage earner divides his amount of wealth into fraction, and theta 0 is the fraction of his wealth that is devoted to the money market, and from theta 1 up to the n, these are the fractions for his wealth associated to investment in the financial market, risky assets in the financial market, so that the sum end up to 1. And so we can reduce this. We can take theta 0 out, because as soon as we know all these, so the complement will be theta 0. So we can talk about reduced portfolio. It's a vector on Rn. Now, the wealth process x of t is going to be the initial, what he has in the beginning, plus what he gets. This is the income, minus what he consumes, minus what he pays to the insurance companies, plus what he gets out of investing in the financial market. Sorry, 3 minutes. Okay, it's good. Now, the controls will be theta and p. P is a vector of premium. So the zero component here means that the guy is not buying a life insurance contract from the KF insurance company. So now what the guy wants is to maximize some expected value obtained by consumption. Utility attains from consumption, plus he wants also to maximize the amount of money that he gets if he die before capital T, and he wants to maximize the wealth if he lived that long. I mean, if capital tau, if tau is going to be greater than capital T. So with these assumptions for U and P and W, it's going to be like differentiable strictly increasing and strictly concave function. We could like write the objective functions J for this guy as using this formula. And if you differentiate the wealth process, you get exactly this one. Now, we define here some probabilities, conditional probabilities, for us to be able to transform our objective function to an equivalent one with deterministic time here, okay? So that's essential assumption for us to be able to use dynamic programming techniques. Otherwise, it's impossible. So these are the conditional probabilities. So the G plus is like the conditional probability for the wage earner to be alive at time S, conditional upon being alive at time t less than or equal s. And G minus is the distribution, it's the complement and the distribution, and this is the density. Now, like that, we could transform our problem now to an equivalent one, but now capital T is fixed. So it's not random variable anymore. Like that, we can use the dynamic programming techniques, and we can define V as the supremum over of J over all the controls. So the controls new here is a vector includes theta and the consumption and the portfolio investment, life insurance. All these are our strategies. So like that, B functions satisfy this recursive relation. Now we can pass on to this Hamilton-Jacobian-Bellman equation, and this Hamilton-Jacobian-Bellman equation is a partial differential equation whose solution is the value function under consideration. And moreover, so V star is going to be optimal if and only if the equality holds. So like that, this equality provides a strategy to find back the optimal strategies in terms of the value function and its derivative using these functions I1 and I2. These are just like the inverse functions because of the smoothness of UP. And so like that, these are our optimal strategies. So the consumption, optimal consumption is going to be this, optimal investment is going to be this, and optimal premium is going to be the maximum between this fraction or 0 if k equal k star. K star means if the guy likes to buy insurance company from that one, k star, and k star is the one that gives the best offer for him. Okay? So here is just an example. If we consider CRA utilities, constant relative risk aversion utility functions, we could write the optimal strategies in terms of these functions. And here we start our proposition. So here are the statement, and here we write our optimal strategies in terms of all as a function of t, and all these variables are defined here. Okay, and just one remark here is that as time change, the insurance company picked by the wage earners may also change, and this happens according to the relative value functions eta, as I said before. So if he doesn't pay the premium, so the contract ends, and he starts a new contract with the new insurance companies. Okay, so I'll stop here. Thank you.
Okay, thank you. Any question?
Just one question. Why do you need to include the financial assets in your model, risky assets and non-risky assets? Can you consider simply the wealth of the consumer, for example, and insurance?
Yeah, so normally if you want to invest in financial market, you put part of your money. So if you are not risk aversion, you put, if you don't want to go for risk, you put all wealth in the money bank, on the money market, in the bank, and then you wait to end of the year to get some interest. But if you like risk, so you divide your wealth, or you may invest all your wealth in the stock market. So if you talk about financial market, I think you can use both.
But I mean that we can have a model without talking about securities and assets.
Oh, you just put the fraction zeros.
Okay, and consider the wealth of the consumer as random variable?
No, these are the fractions, so you decide. So it's your money, so you decide how much money you invest in the money market or in the stock markets. You divide the fraction of your wealth. So if you put the fraction 0 for the case, like stock plans, so you don't invest in that direction, you invest in other directions. Thank you.
Okay, thank you. Now, Dr. Abdullah Hakawati, interpreting of cone metric space via renorming the Banach space.
السلام عليكم. شكرا مرة ثانية. Thank you for being patient to see me twice today. شكرا. بارك الله فيك. بارك الله فيك. In the morning, we were seeking a generalization of cone metric spaces, and we were almost arriving to what we call normal cones with normal constants. And the necessary details were missing due to probably overlooking the time limit. All necessary details are somehow going to be included in this talk. Precise, hopefully, precise, concise, accurate, and formal. At the very end, we are seeking to normalize the normal constants for normal cones to 1. We will normalize to 1 the normal constants of normal cones. This is our final objective, and that is accepted for publication in the Journal of Nonlinear Analysis and Applications. My friend, my student, an MSc student, تفضل يا هيثم. He will take the job.
So I will start by introducing myself. I am Haytham Abu Sarris, a master student. My supervisor Abdullah Hakawati, and I will quickly, as possible, introduce my subject, what was titled by Cometric spaces. Banach space, as familiar with Banach spaces, is a complete norm space. I mean, every quotient sequence are convergent. Our main subject cone, if we let B, if we let E be a real Banach space with a norm, a subset B of E called a cone, if the conditions are satisfied. These conditions, B is non-empty, convex, closed, and non-trivial. The second condition, the linear combination of x and y with a non-negative constants is in B, and the third condition is the non-negative of elements of B. Okay. The Banach space is partially ordered by the cone as follows. First of all, x is this or equal y, and only if the difference between y and x is in B, and x is behind the y if the difference is in the interior of B. Finally, if x less than y means that x less or equal than y, but x not equal y. This is the partial ordered by the Banach space. Examples of our cone in R, the non-negative numbers form a cone. This is our picture. In R2, any wedge from the origin to infinity forms a cone. In R3, the same thing. In general, but we will focus to the negative of items of cone. Another example of the summable sequences, non-negative summable sequences form a cone in the LB spaces, including L infinity. And finally, the continuous real valued functions form a cone. We go to the properties of cones. We have normal cones, regular cones, menhedral cones, strongly menhedral cones, and finally solid cones. Just satisfied for each one. Normal if there exists a constant k greater than 0, such that x between 0 and y implies that the norm of x less than or equal k of the norm of y. This k is the normal constant of the cone B. We have the magnitude of k is not less less on 1. There is no cones with constant less than 1. The related to the sequences. If every increasing sequence which is bounded above is convergent, equivalently the decreasing sequence which is bounded below is convergent, then we talk about regular cones. Menhedral, to define the soup of two items, if soup of x, y exists, then this cone menhedral. And strong menhedral if every subset of A which is bounded above has supremum. And finally, the solid if the interior P is non-empty. Important lemmas related to what? In A, the Banach space. Banach space. If the supremum exists, then we talk about menhedral cons. بالضبط. soup. Non-existent. Non-existent. In R2, x0.
Yeah. Okay. Your partial, excuse me, your partial order is not total. In other words, there might exist two elements which are not comparable. You are not talking about chains. You are not talking about partial, total, partial order. No, I'm not assuming that they are comparable. I'm not assuming by no means that every two elements are comparable. Not every two elements are comparable. And I'll give you the non-existent supremum of two elements. It means the supremum is the least upper bound. It's the smallest. It is the thing which is greater than all of the elements, but less than anything that is greater than them all. It's the least upper bound in terms of that partial order. The supremum is the least upper bound. And upper bound is the thing that is greater than or equal to all of the elements of the set. The least such, if it exists, is called the supremum. If it exists, sometimes it doesn't exist. For example, let me show you this. The supremum of two vectors is the supremum of two vectors. The supremum of the set consisting of the two vectors. Doesn't that make sense, gentlemen, ladies? What do we mean by the supremum? The supremum is just like what you wanted in analysis. If it No, I'm not saying the supremum of the vectors is bigger. I'm saying the supremum of the set of all two elements, of all sets with two elements exists. I'm not sure if I'm What do you mean by saying that x is less than or equal to y? What do you mean by saying x is less than or equal to y? So, x is less than or equal to y means that y minus x is in the cone. So the supremum of the set is an element which is larger than or equal to each element in the set. So if you subtract any element from that, you stay in P. Perhaps this this is a sophomore student. I mean, a student. What do we mean by the soup of E? What's the soup of E? This is the least upper bound of E. I'm not sure if there is a misunderstanding. Maybe there is a misconception.
Okay, let's continue.
Okay, after the session, okay? Okay. Okay, we have limited time, so after the session, okay? Continue.
Okay. Quickly, I just mentioned the important lemmas related to the properties. There is not normal cone with normal constant less than 1, and for each k greater than 1 there is a normal cone with the constant m greater than k, and every strongly menhedral normal cone is regular. Every regular cone is normal, but not conversely. There is a normal cones, but not regular. And here is example to illustrate lemma 5, normal cone, but not regular cone. Now, cone metric space is the same of the metric one, but we replace the codomain by Banach space. It was R, real numbers, and it became Banach space. Then we call it cone metric space. Example of cone metric space about summable sequences, non-negative summable sequences, in LB. And here is the definition of convergent Cauchy sequence and complete cone metric space, the same definitions of the ordinary one, but we replace epsilon by C. You can be familiar with this definitions. Now, cone norm space, the ordinary is norm space, but we replace this by R by Banach space and the same conditions. Then we get a cone norm space and absolutely cone Banach space. And every cone norm space is a topological space. This is the topology of cone norm space, and this is the vertices. Okay. If our cone is strongly menhedral, then we can define the continuous function. As you see, the same definition, a map T is called continuous at x. If for each v in T containing T of x, there exists U in TB containing x such that T of U subset of B. Okay, this is our main result. Meterizability of cone metric space. The important question is, are cone metric space equivalent to metric 1 or generalization? This is the part of answering this question. Many of authors, Mr. Khan and Bourmadi, improve the meterizability, and this is this is the theorem of theirs. This is the form of the equivalent metric space to define the cone metric, the equivalent. Mahdi Asadi and others try to prove the meterizability, and this is the definition. Moreover, Mahdi Asadi give the procedure of renorming the Banach space to define the equivalent metric by renorming the Banach space, and this is the new norm. But unfortunately, this is the theorem was disproved, and this motivated us to more investigation in renorming Banach spaces, and we get a new result. This is lemmas helping us to prove our new norm. Lemma 1 to prove the triangle inequality, and lemma 2 to prove the normality. This is our theorem, and this is our new norm to define the cone metric space. The norm of infimum of the upper bounds, and the norm of supremum of the lower bounds. We prove that is a norm by justifying the three conditions. X is equal 0 if and all if x equals 0. The negative of x, norm of negative of x equal norm of x. For each alpha greater than 0, norm of lambda x equal lambda multiplied by norm of x. And finally, the triangle inequality using lemma 1. We have it. Norm of x plus y less than or equal norm of x plus norm of y. And using lemma 2, we prove the normality with the constant k equals 1. And the final result is that consequently due to this approach, we prove that every cone metric space is really a metric 1, and every theorem in metric space is valid for cone metric space automatically. This is.
Okay, thank you. I'm sorry, no time for a question. Doctor, after session, no problem. After session, no problem. We have time. Is method for solving local fraction Friedholm integral equation by Hindiswaith, Abdullah Zekan, and Iyad Suwan.
My name is Hind Khalid Swaz from the Arab American University. The presentation titled is Local Fractional Fourier Series Method for Solving Local Fractional Friedholm Integral Equation with the researchers Dr. Abdul Halim Zekan and Dr. Iyad Suwan. In this work, we study the local fractional Friedholm integral equation, and we solve this equation using the local fractional Fourier series. For this work, we study at first the local fractional calculus, which is a branch of mathematical analysis that deals with derivatives and integrals of arbitrary orders. It has many applications in physics, chemistry, biology, in engineering, economics, also in applied mathematics. It solves many problems in local fractional, ordinary, and partial differential equation, local fractional Fourier transform, and fractal signals, and other fields. We study the local fractional Friedholm integral equation and some methods in literature like the Newman series method and the Adamian's decomposition method. Also, we study the local fractional Fourier series of one dimension and give new examples about it. Then we derive the formula of the local fractional Fourier series of two dimension and give applications on it. After that, we use the local fractional Fourier series of one dimension and two dimension to solve the local fractional Friedholm integral equation of the second kind. The local fractional derivative, if f(x) is a fractal continuous function on AB, then the local fractional derivative of the function f(x) can be given by d alpha f(x) node at x equal x node, d alpha f(x) node equal to f(x) equal to limit delta to the power alpha f x minus f x node over x minus x node to the power alpha, where x goes to x node. If the limit exists, then we say that the function f x is a local fractional analytic function. Here we solve, we find the local fractional derivative for some local fractional functions using the definition of local fractional derivative. The local fractional integration, we say that the function f(x), the local fractional continuous function f(x) on the interval a, b, we can find the local fractional integral by this formula. Also, we find the local fractional integral for some functions. Then these integrals will be used in next examples. The local fractional Fredholm integral equation, the standard form of the local fractional Fredholm integral equation is u of x equal f(x) plus lambda to the power alpha over gamma 1 plus alpha integral from a to b k of x with t ut dt of order alpha, where u of x is the unknown function, f(x) is a continuous function, lambda to the power alpha is a parameter, the limits of integration a and b are constant, k of x with t is the kernel of the Fredholm integral equation. We study two methods for solving the local fractional Fredholm integral equation of the second kind in literature. The first one is the Newman series method. The strategy of the Newman series methods starts by setting u naught of x equal to f(x). Then to find u1 of x, we substitute u naught x on the integral equation, and then find u1 x equal f(x) plus lambda to the power alpha epsilon x, where this is the formula of epsilon 1 Lx. Then continuing in the same manner, we substitute u1 to find u2 of x. Then the result u of x will be on the form u of x equal f(x) plus lambda plus sigma from n equal 1 to infinity lambda to the power alpha epsilon n of x. Also, we study the Adomian's decomposition method. This method is similar to the Newman series method. It starts by setting u naught x equal to f(x), but then u of x can be found by the summation from n equal to 1 to infinity u n Lx. The local fractional Fourier series. We study the local fractional Fourier series of one dimension. At first, we have the local fractional Fourier series representation of f of t in the generalized Hilbert space. F of t equals sigma from k equals 0 to infinity, phi kt, where phi k is the coefficient of the local fractional Fourier series. So we can approximate f of t by taking the partial sum from k equals 0 to n of phi kt. Also, we have the trigonometric Fourier series of f of t, which is given by f of t equal a naught plus sigma from k equal 1 to infinity ak cosine k w naught t to the power alpha plus sigma k from k equal 1 to infinity bk sine k w naught t to the power alpha, and the coefficients a naught, lk, bk can be found by these integrals, and w naught equal 2 pi over t. In this example, we expand the function f of t equal t to the power 2 alpha, where t between minus L and L. We expand this function using the local fractional Fourier series form. This is a naught, we get, this is lk, and bk equal 0. Now also we derive the formula of the local fractional Fourier series of two dimensions in a similar way as the Fourier series of two dimensions. We do the same procedure to derive the formula of the local fractional two-dimensional Fourier series. We use the complex form of Fourier series of two variables, where we take the function f of x, y of two variables, where x is on the period 0 t1 and y is on the period 0, t2. We take all cases when m and n are both positive or both negative, or one greater than 0 and the other less than 0, when one of them is 0 and the other greater or less, or when both of them are zeros. We have these coefficients. And this is the formula of the of the two-dimensional local fractional Fourier series, where W1 equal 2 pi over T1 and W2 equal 2 pi over T2. These coefficients have the following forms. When n and m not equal to 0, we have AMN, BMN, CMN, DMN. When m equals 0, we find EN, FLN, and when n equals 0, we find GM, HM. If n and m equals 0, we find A0, 0. Here an application of the local fractional two-dimensional Fourier series. We have the function k of x with t equal x to the power alpha t to the power alpha. This is a function of two variables, where x between minus pi and del pi and t to the power alpha between minus pi and pi. We expand this function using the previous formula. All the coefficients equal to 0 except dmn. So the local fractional Fourier expansion for x to the power alpha t to the power alpha can be given by this series. Now we use the local fractional Fourier series of 1 dimension and 2 dimension to solve the local fractional Fredholm integral equation. We expand the functions on the Fredholm integral equation, FLX into its local fractional Fredholm integral into its local fractional Fourier series of 1 dimension, and we expand U over X into its local fractional Fourier series of 1 dimension, and we expand K over X with T into its Fourier series of 2 dimension. After that, we substitute these Fourier series on the Fredholm integral equation, and by integrating each term on the integral and equating both sides of the equations, we can find U naught, UI star, UI, and write the formula of U over T. For example, if we have U of X equal to gamma 1 plus alpha plus 1 over gamma 1 plus alpha integral from 0 to 1 x to the power alpha ut dt of order alpha, we want to solve this equation using the local fractional Fourier series method. F of x equal to gamma 1 plus alpha, which is written in Fourier series form, and we have the kernel x to the power alpha. We transform x to the power alpha into its local fractional Fourier series. We write u of x into its local fractional Fourier series. After that, we substitute these series on the integral equation, and by integrating each term here, we can get the u of x by equating both sides of the equation. Then u of x will have this formula, which is the same formula we have get using the Newman series method. Thank you for listening.
Thank you. Any questions? We have meeting at this room. Okay.